was 3. But if you're at 100 FPS, for instance, and let's imagine that the render queue max is 3 frames, that's 30 milliseconds on render queue alone. Yeah,
right, yeah.
Which can be pretty substantial. I'll show you how that can mean the difference between hitting a shot or not. The last piece is GPU render. So this is the simplest thing to visualize. This is where it's rendering a frame pixel by pixel. All the coloring takes place here. But this is actually the most important one because it's dictating the timing of everything before it. It dictates whether the stages before it get unblocked or not. This is the same animation. But when you're GPU bound, the latency for GPU render is simply equal to 1 frame time. So let's do a GPU bound example at 100 frames per second. So that means that frame time is 10 milliseconds. Let's assume that reflex is off. I'm making this distinction.
It's basically native.
Yeah. I'm making this distinction because the traditional GPU pipeline is built for FPS throughput. And when reflex takes over, that pipeline kind of changes. Because when you're GPU bound, that same pipeline kind of fails for latency. So we'll do reflex off first. And let's assume that simulation takes 3 milliseconds, which is pretty common. So this is what it looks like. You have a frame on GPU render, you have a frame on the render queue, you have a frame that's starting simulation. Let's move that along. So this is pretty simple. This is how the pipeline goes. So if we try to put numbers to it.
Okay,
right?
yeah.
So we said input sampling is half the frame time. So that's 5 milliseconds in input sampling alone, right? For simulation, we know that this is going to take 3 milliseconds.
I have a question about that. So is it collecting input data for the entire 5 milliseconds in this example? Or is it sort of like that's the time it takes to actually process?
That's the time it takes to actually process.
Okay, so it's already collected it, I guess, at a single point in time?
Yeah, so it just depends on when that input is going to be carried over to the next stage of the pipeline.
Got it.
So here you have 5 milliseconds. The CPU simulation is going to take 3 milliseconds, but here's the thing. It can't submit to the render queue because it's stuck. So you have to wait, right? You're going to have to wait for a frame time to happen. So that's 10 milliseconds there. We have a frame in the render queue, so that's another 10 milliseconds. And then we have a frame in GPU render, so that's another 10 milliseconds. So here, your PC latency alone is 35 milliseconds.
And then for total end-to-end, in front of all this, you have input. Behind all of it, you have display.
Yeah.
And that's the total, I guess.
Yeah.
Okay.
So if I had to put some numbers to it, let's imagine, 1 millisecond for peripheral, it's 36, and then another 5 or so for 144 hertz of refresh rate, so that's at 41. And I'm being kind here. This is the best case without reflex intervention. It's just 1 frame in the render queue. So we can see how it changes with reflex on. What reflex is doing is it's attempting to remove those stalls in the process and speed up or ensure that the delivery of the frame is the latest frame, right? So we're going to do the same exact thing. So it's going to be GPU bound at 100 frames per second. So your frame time is still going to be 10 milliseconds. Reflex is on and simulation takes 3 milliseconds. So let's imagine that you have a frame in GPU render. So what we'll do is while the GPU is starting the render, we're actually going to hold frame 1.
Okay.
We're going to prevent it from starting simulation. And we're going to hold it for 7 milliseconds.
Is that
in this particular example?
Okay, so it's
just a particular
based,
example.
Okay.
This is a dynamic algorithm. And so the reason for that is because we're going to hold it for 7 milliseconds while the GPU is rendering for 7 milliseconds. And then once those 7 milliseconds pass, I'm going to allow frame 1, the new frame, to start simulation.
Is hold time equal to time in GPU render?
Yeah,
okay.
So not necessarily. It adjusts depending on the load.
Okay.
But the reason why we're holding for 7 milliseconds in this example is because that means that GPU render has 3 milliseconds remaining to finish. And then we know that simulation takes 3 milliseconds, right? So now they're synchronized. The CPU and the GPU are synchronized. And then when those 3 milliseconds elapse, it just passes through.
Yeah.
You're bypassing everything. And then it starts again. And so if we put some numbers to it, your sampling latency is going to be the same. It's 5 milliseconds. Here, in CPU execution, since you have nothing holding it up, if simulation takes 3 milliseconds, your CPU execution latency is only 3 milliseconds. Your render queue is empty now, right?
Right.
So your render queue latency is close to 0 milliseconds.
At any stage with reflex, does the render queue come back into play? I mean, are there situations where it ends up getting utilized again?
Yeah.
Okay.
So, I mean, but this is on purpose. So we set particular targets such that the render queue is not empty, and this is just to ensure that frame delivery remains smooth and consistent. Yeah. And your GPU execution remains the same at 10 milliseconds. So in this example, your PC latency is now 18 milliseconds, and latency has been reduced. This is the last one. So just to summarize, so we need to understand how the game engine works to reduce the latency to the extent possible.
If you're not executing at a game level, like an engine integration level, and you know, we're not going to get into the whole VAC bands thing with anti-lag. Not the purpose of going down this path, but what are the steps of trying to execute globally, assuming there's no type of anti-cheat issue? If you try to execute globally, there's something else in the pipeline between, say, a driver level versus an engine. So what is that piece?
So that piece, an example of that piece would be something like ultra low latency mode in the driver.
Okay.
And so the latency reduction there is not as good as reflex, because really all it's doing is it's attempting to empty the render queue, but it's not necessarily syncing up the CPU with the GPU such that the frame delivery occurs just in time.
I see.
And so from the driver level, you're kind of constrained on the best you can do. So that's one piece. And the other piece is that you just really want to understand how the game engine works and work with developers to optimize to the extent possible.
Okay.
So that's what it does, right? So it synchronizes the GPU and the CPU, it empties the render queue, it behaves like a dynamic frame rate limiter, and even though we're pacing the game, in practice it should have virtually 0 FPS impact. But it's normal if it affects FPS somewhere between 1 to 3%. I think that's normal. Even in our QA process, for instance, if it's higher than 3%, we actually flag that as a bug, and we go back to the developers and say, the FPS hit is more than expected. But ideally, even if you do get a 3% FPS hit, it's more than compensated for the reduction in latency.
Yeah, so I was going to say, theoretically, you should still have better latency, even with FPS drop, which is where we get back into the like methodological discussion for our GPU reviews, things like that, of FPS, especially as it becomes comically high. FPS average has never been the full picture. Frame time has helped reviewers solve a lot of that. There's a little more to it, you know, like GPU busy, MS GPU active, present mon. But latency helps to look at, I guess, more maybe experiential as opposed to just pure throughput. Or
There's
speed.
a dimension that's missing there, and that's responsiveness, which is really, really important.
And that's going to be it for now for this one. We have a lot of latency testing that we're starting to introduce. We debuted it in one of our reviews recently, and we're planning to make it a part of at least the GPU reviews, if not CPU and GPU reviews, because we think this is an important metric up there with frame times for review data. And so we're going to start including that. You'll see a methodology piece sometime following as we continue to work on this, and you'll also see a part 2 featuring Nothing. He's a Counter-Strike pro who helped provide us some data at a very high level of play so we could work with what our goals are for latency testing. Thanks for watching. Subscribe for more. Check out some of our other interviews with experts in the industry if you want to learn more just from an educational standpoint, and we'll see you all next time. This factory sounds like a coin-operated arcade. And all of these massive buildings filled with massive machines make this, a bearing. We've seen how computer fans get made in the past. But we've never seen how the parts of those fans are made. This highly specialized factory makes a part that's commonly faked in case fan marketing: high-end fluid dynamic bearings. They wanted to show us how the real ones are made, since so many companies claim to use FDBs, but when you tear the fans apart, they just use sleeve bearings. This factory makes millions of FDBs and ball bearings per year, and they're a major supplier for quality bearings and computer case fans. We went all the way up the supply chain this time for this special look behind the scenes of how parts are made. This Taiwan-based factory makes fluid dynamic bearings for Lianli's most expensive case fan. The factory is owned by TPI Bearings, which makes not only fan bearings, but also angular contact ball bearings for machine tools, deep groove ball bearings for general use, fluid dynamic bearings for servos and robotic arms, TD strainwave drives and joints, and even bearings for gigantic construction machinery. In fact, the largest bearing in this lobby was the size of an entire case fan, about 120 millimeters. In this special edition to our latest factory tour season, we'll see how ball bearings and fluid dynamic bearings get cleaned of debris and greased for use, and how they're optically scanned and carried away on automated conveyor belts. We'll show how they're ground and prepped, and we'll get an educational opportunity to learn about the differences between these two types of bearings. The last part of the tour will focus on FDBs specifically, which are one of the most expensive parts for PC case fans. Let's get started with this educational deep dive into case fan bearings. Before that, this video is brought to you by the Deepcool AK620 digital air cooler. We previously reviewed the baseline AK620 as a strong performer and extremely price competitive. Now, the new digital variant includes a screen with a display for some extra flair, including CPU temperature and high temperature warnings on the display. If you liked the AK620's performance but wanted more visual pop without going liquid, consider the AK620 digital at the link in the description below. This is the factory. It's aisles upon aisles of equipment with conveyor belts running all the way up to the ceiling and around the facility. We'll start with the life cycle of an angular contact ball bearing. First, an explainer. Angular contact ball bearings, or commonly shortened to just ball bearings, typically use steel balls, ceramic balls, or a mix of carbon and chromium to roll between an inner and outer raceway, or rings. High precision rolling elements need to be manufactured to fine tolerances to ensure precision and stability of rotation, especially at high speeds and heat, and the bearing has to be packed with grease to encourage low friction rotation. There are many types of grease for use in different applications, ranging from high heat automotive to relatively low heat spindles. The inner race has a groove, or sometimes a special deep groove, in which the balls roll. A cage or retainer is used to separate the balls and keep rotation smooth. The cage has a big impact on noise emissions as well. To prevent lubricant from leaking, most ball bearings also use shields or seals of rubber, and they also double as protection against contaminants. Ball bearings typically develop fatigue within the raceway or rolling element with age. Commonly, the rated L10 lifespan, or the minimum lifespan of 90% of the bearings, is 50,000 hours. Depends on the application. Common pros of a ball bearing include cost efficacy, versatility, and strength in high-speed applications. They're also low maintenance with shielding, and relatively easy to maintain when necessary. Common cons are limited load capacity, where the rolling element can deform under weight, noise levels at high speed, and particularly when the grease dries, heat at speed, and sensitivity to contaminants. Now that we have some basics, let's go to the factory. We're starting with the ball bearing part of the factory. Each angular contact ball bearing line is manned by just one person, and is capable of producing 100,000 complete ball bearing assemblies per month. The factory is equipped with multiple of these lines, spanning several floors. The line starts with an exciting, bright red beam that looks almost molten. This optical inspection machine is the first step in the process. It gets fed from a hot heat at speed, and sensitivity to contaminants. Now that we have some basics, let's go to the factory. We're starting with the ball bearing part of the factory. Each angular contact ball bearing line is manned by just one person, and is capable of producing 100,000 complete ball bearing assemblies per month. The factory is equipped with multiple of these lines, spanning several floors. The line starts with an exciting, bright red beam that looks almost molten. This optical inspection machine is the first step in the process. It gets fed from a hopper that contains a supply of inner and outer rings, or raceways. They're not assembled yet. This automated process carefully scans for diameter, done by using an arm that shoots down to hold the component in place while a laser scanner analyzes the size. Tolerance can be tuned for the customer, but these bearings are inspected to a tolerance of 30 microns. Any defects are sorted aside for manual inspection to see if they're salvageable, and if not, the metal is sold to metal recyclers. The defect rate of step 1 in this process is 1 in 1,000 units, or 0.1%. As bearings pass, they're pushed with a robotic arm onto the oil-covered slipway that brings them to a mechanical counter, which simply ticks up for each new part. And then they progress down the slide into a tiny lift for bearings. This goes up to a track that leads to the second stop in this line, the grinding machine. Looking at the grinding machine in action through this protective glass, it does exactly what the name suggests. The machine grinds down the rings to begin smoothing them out for their future low-friction application. This process takes 10 seconds for each of the smaller products and 30 to 40 for the larger one. One unique challenge of the grinding process is that it magnetizes the parts, so the components run through a demagnetizer before proceeding. Like clockwork, each ring follows these steps, dumping oil with each one spit out. The oil gets recaptured in a pan under the machine, filtered, and then reused later. The apex of the line runs through an oil bath, which helps rid the race of any debris from the grinding process and then relubricates it. Then, just like before, they progress over to another vertical lift and travel up and over to the next machine. That's where we get to the most important part of this process: polishing. The polishing process follows the grinding and oil bath, getting a perfect finish to the surface. After polishing, some bearings are spot checked at a manual inspection station. This involves tools like a magnifying glass and measurement gauges or calipers to measure the surface smoothness, the diameter, and the finish. And as they progress, once again, the bearings end up back in the lift and they're brought up to the ceiling, over to the next room, through another 10-second oil bath in a box, and then to the ultrasonic cleaner. Here, the smaller rings are held in place for about 8 seconds at a time and then advanced on the track, while the larger ones take longer. These ultrasonic cleaners use cavitation bubbles from high-frequency sound waves to help dislodge debris and dust. When the bubbles pop, debris is removed and swept away by oil. TPI says that dust is the #1 cause of failure for bearings, which is why they have so many cleaning steps at every stage in the pipeline. Oil is regularly changed at this stage, and it's sent through filters like these, which help trap contaminants at multiple filtering stages to reduce the use of new oil. In the background of the ultrasonic cleaner and the filter, you can already see the next machine working, and it's completely custom built for this job. This machine is one of the most mechanically active. Its job is to match the most suitable inner and outer race to each other. Due to the 30 micron tolerances previously, the over-under of the inner and outer rings means that they can't just be combined at random to have a high-quality ball bearing. Instead, as each ring enters the machine, fresh from the ultrasonic cleaner, a robotic arm moves in, extends down, and expands a physical gauge acting as calipers to measure the inner and outer diameters. Then, the central robotic arm picks up the ring and either places it in the middle, acting as a holding area until a perfect match is found, or places it to the side nearest the exit, and that's with its match. Like a matchmaker, the arm creates a memory and knows the tolerance of each individual ring it picks up. It then tracks its location in memory until the perfect match is discovered. This reduces defects, eliminates guesswork, and increases precision. For the parts being made today, the inner to outer range of mating tolerance is 13 to 29 microns, so they have a 16 micron gap within that original plus or minus 30. Imagine getting swiped left on because you were 31 microns the wrong height. It's a very judgmental robot. If any bad raceways are found at this stage, they're set aside in a different holding area to be reclaimed or recycled. The paired inner and outer rings next exit the machine and have the steel balls placed roughly between them. However, the balls can't fit within the inner and outer ring yet due to the tolerances, so they sit only partially lowered into their final location with the seal applied. The unit progresses to a heating coil, where it heats all the components up enough to loosen and expand the rings, which allows the rolling elements to fall into place within the complete ball bearing unit. The bearing only needs to sit within the coil for 4 to 5 seconds as it gets blasted with heat, making this one of the most efficient parts of the process. Watching this machine work is impressive. And now for the final steps of the ball bearing manufacturing process, starting with photography. Here, the assembled angular contact bearing proceeds to a dark chamber for some quick flash photography. This serves as another optical inspection step, where the machine is checking the photo for accurate placement of all components. It also saves the image and presents it on the screen for human quality control operators to inspect. As the bearings exit, a series of pistons work to punch the bearings over to the correct track, depending on whether it passed or failed AOI, and then they get cued and punched into the next conveyor belt. Failure rate for completed units at this stage is under 0.1%, and the factory was able to achieve this by building its matchmaking robot that we saw earlier. This also helped them lower costs to customers by producing with higher yield. They follow this belt to another demagnetizer, which holds each bearing assembly temporarily to ensure it isn't magnetic. Then an intense oil bath and ultrasonic cleaning stage ensues once more to ensure the bearing is prepped for the final stages. After this, there are 8 more stages of washing for the bearing, this time progressing through a completely custom-made machine for the job. You can see the bearings get moved one stage to the next by these black clamps. Each stage involves a spraying head that lowers down over the assembly, which blasts it with high pressure to fully clean out the channels. These tools then rotate the bearing assembly during the process to make sure it's fully clean. The nozzle then raises, the bearing is grabbed, physically moved to the next nozzle, and blasted again. It happens 8 total times until it's ejected back onto a lift, where they progress up and over into the next machine. There's one last intermediary optical check, and then the bearings are dropped as if into a slot machine down this ramp. Like the world's lowest friction Plinko machine, this complex set of robotics performs a few steps. First, it checks the diameter once more and logs it. Then it performs a wash to remove some of the excess oil from earlier. Then it applies a special anti-corrosion formula, a lot of this not visible externally. And finally, it fills the bearing with grease and packs it together. The process is quick, at only a few seconds per bearing assembly. After all these steps, you can see the trays upon trays of bearings as they're sorted by size and type. And that shows the entire process of how the angular contact ball bearings are made. It's a lot of cleaning, conveyor belts, and optical inspection, with critical steps for grinding and polishing. But now, it's time to move on to the next stage. Next up, testing. We walked across the factory grounds and proceeded to the secure room where TPI's engineers do R&D and testing of their products. In this room, you'll see fans and petri dishes with bearings and oil everywhere, often accompanied by a pixel art smiling thermometer indicating humidity and temperature and suffering. There are various types of environmental and thermal chambers here where TPI lets racks of new fans and exposed bearings sit in programmed conditions. This allows them to test for the impact of humidity and heat for longevity and endurance testing. Here, newly engineered fluid dynamic bearings are being sent through a drying oven at 120 degrees Celsius, with the company planning to move to 200 degrees in the future. Unfortunately for these bearings, their entire existence is to feel pain. They get made, and then they get tested until failure. Some of the endurance testing includes observing and occasionally sampling the oil in trays for chemical changes due to prolonged exposure to simulated elements. This is to double check that the oil's characteristics, such as viscosity and dry out endurance, are the same as in the CFD simulations. FDBs often use 2 different kinds of oil at different densities, so each of these is tested here. But in addition to product endurance testing, which is mostly done with rapid heating and cooling to simulate age at a faster rate, they also do real-time R&D testing. One of these ovens is used for research, and it'll be testing at 60 degrees Celsius for 100,000 hours. It's been running nearly continuously for years now, and it hasn't had a failure yet. Although this can be simulated to keep things practical, and it is, they still maintain some real-time ovens to check those simulations, even if it'll take a decade. For completed products, typically if anything fails, it'll be the electronics, the motor, or the circuit board. If a fluid dynamic bearing fails, it's normally from oil leakage or dry out. Now to get into FDB R&D and manufacturing, first some more basics. Fluid dynamic bearings are non-contact bearings that are typically quieter and steadier in operation as a result of their use of fluid. These get their name from the fluid in which the shaft rests, which, as it spins, pressurizes the fluid. FDBs are made of a few key components: the shaft, or the rotor, which is connected to the motor spindle, and the FDB inner surface is one of the key areas that gets designed. TPI machines its FDBs with a V groove, which is shaped just like it sounds. There's also the stator surrounding the shaft, commonly made of aluminum, brass, or bronze, or stainless steel. The fluid itself supports the load and, during rotation, forms a thin film between the shaft and the bearing housing. Grooves help to distribute this film evenly and at as low an RPM as possible. Finally, a return circulates the fluid and helps with heat dissipation. This room helps illustrate the components. The benchtop power supply, laptop, and test platform are configured for testing the voltage of the bearing to the fan shaft. As a demonstration, we see the voltage drop when the rotation stops or slows, which is due to friction or contact between the FDB and the shaft, especially in the resting state. By using voltage, this lab can evaluate the oil pressure within the FDB during operation, but without disturbing it. This R&D lab is trying to determine how the bearing behaves internally at different speeds, and so using these instruments gives it an inside look while preserving the integrity of the bearing. Now to the last leg of the tour, manufacturing of FDBs. While walking over to the FDB factory, we get a large reminder of just how many things have bearings. These spinning mini wind turbines are dotted around the campus, and for good reason. It's windy here. TPI makes the large bearings found in these power-generating wind towers that help generate power for use within the campus. These also serve as R&D for TPI, as it can observe the longevity of its bearings on site. And now we're entering the FDB factory. Most of the steps are familiar to what we saw with ball bearings, which is why we went over them first. There's really only one key difference, and that's processing the metal and also filling it with fluid, where they take a supply of metal rods and cut them down to size. We asked our community for some information on this machine since it was lost in translation, and viewer Calvino Bear wrote this. Quote, "That's a bar feeder, probably for a Swiss-type lathe or screw machine to make the bearings. It feeds bar stock into the lathe's cullet chuck while the chuck is unclamped, usually with some kind of pneumatic cylinder, into a stop in the machine. The lathe reclamps, and then it can make a new part from this fed-in material. It allows the machine to run almost completely unsupervised, making thousands of parts a day." And thanks to viewer Mr. Bear for that one. As the rod gets fed into the machine, it's chopped to size and spit out into a collection bucket. This eventually forms the housing that you can see in our completed FDBs we were allowed to take home as souvenirs. The rest of the FDB manufacturing steps are similar to the ball bearing steps. There's a lot of cleaning and conveyor-ing, and the secrecy around the fluid aspect meant we couldn't film that machine. After the bearings are completely manufactured, they go through desktop ultrasonic cleaners to remove debris once more, and then they get packaged in plastic and visually inspected. This room also serves as QC, where they take random samples and cut them in half to inspect the grooves. And that completes the bearing factory. This has been an incredibly educational journey into learning not just about how bearings are made, but how they work when different kinds are used. This has been our 4th weekly installment in our newest season of factory tours. Last week, we visited an engineering lab to learn about custom circuit board design for specialized tasks. Before that, we visited a RAM manufacturing and binning facility, and before that one, a server and case manufacturing plant to kick this all off. Next week, we're taking a brief break from this series, and then we'll come back with a couple more episodes to close out the season. Subscribe to catch more of our educational factory tour series, and let us know what kinds of factories you want to see next. To support us and this educational series, go to store.gamersnexus.net and grab one of our brand new Disappointment Build 2023 shirts. We only made one run of these, and we're already more than halfway through. We don't plan to restock them, so visit the store to pick one up today and support our series. Thanks for watching. We'll see you all next time.
I need a new travel mask and a travel router. Tomorrow, I'm taking my wife and 6 kids to Japan. Like, we're leaving in the morning. And I'm realizing right now, in this moment, that the travel mask and router I made for my last trip isn't going to cut it. It's gotta be faster and smaller. I've got more kids and I gotta take it on a plane, and Japan, and And I wanted to do a lot of stuff, like stream Plex to everybody, operate as a really awesome NAS so I can back up my vlog footage as I'm traveling to my studio so my editors can edit it. And I want to add some fun little Docker containers and VMs along the way because I'm extra. So here we go. I'm gonna speed run creating a travel NAS and travel router now before I leave in the morning. I don't know if this is gonna work, but test it with me. Get your coffee ready. Let's go. Now, if you were here for my last projects, I built a Raspberry Pi router as my travel router. It was running OpenWRT, it was amazing, kept me connected and safe on the road. It was a road trip. I also made a travel NAS out of a Raspberry Pi. This was running Open Media Vault, and it was actually pretty great. It did the one thing I needed it to do, and that was back up my files to my servers here at the studio. Now I've got a lot more things I want to do, and I don't think the Raspberry Pi can handle it. Now maybe the 5 can, but honestly, I'm kind of full of Raspberry Pi. I've had too much. I want to try something new, and something I think is more powerful and maybe more fun. So I looked in my closet to see what I might have laying around. Companies do send me stuff, and I saw something that I kind of heard a lot about already. You may have seen this before. Check it out. Where'd it go? This guy. I'm sure you've seen this, right? It's the Zima board, or the Zima board. I'm not really sure how you say it. This thing is kind of a beast. Here it is compared to the Raspberry Pi 5. Not much bigger, and it's already in a case. But here's what got me excited about it. This thing is not ARM-based, it's x86, which means we can do so much more than we can do with the Pi. We're not limited to like Open Media Vault and OpenWRT. Like, check this out. Here are the specs of this thing they sent me. And by the way, Icewhale, the company, they did send me this. It was free, no strings attached. I forgot about it until now. They sent me the 832 model, which means it has an Intel Celeron quad-core processor. It's got 8 gigs of RAM, 32 gigs of onboard storage. This is dumb. And by dumb, I mean amazing. It has 2 SATA connections. Are you kidding me? I want to build a NAS and it's got SATA connections? I'm already drooling, but check this out. 2 Ethernet ports, USB, yeah, we got that. But man, a PCIe port? Look at this. No, it's kind of weird. It's like sticking out on the side, like a wound, I don't know. But I can do stuff like this. Maybe I want more USB ports. Bam. How about a 10 gig NIC? Sure, why not? How about a whole bunch of ports? Or even, and this is what I got really excited about, Wi-Fi 6? Look at this thing. That got my wheels turning. Wi-Fi 6 router. Can we make this happen? Then I'm factoring in this, hold on. Nested virtualization. Can I install Proxmox on this? Yes, you can. And after I heard that, I mean, I don't care about anything else. I had to try Proxmox, so I did. Hey, Chuck from the future here. I'm back from Japan. And let me tell you, throughout this process, I would have been nowhere, stumbling in the dark, flying blind, without skills I learned from training at places like IT Pro by S.i.R. They are the sponsor of this video and one of the reasons I can do any of the stuff I'm doing. Like throughout this video, networking, Linux, virtual machines, storage, all essential skills you need to do stuff like this, you can learn from IT Pro TV. And it's not just skills for lab stuff, it's skills for life, for jobs. You can turn these really fun things you're learning into a career, a life-changing career like I did. So if you're just getting started, man, check out the A+. Get a good foundation in IT, and then move on from there, advance your career. Learn networking with the CCNA, learn some Linux or cloud or ethical hacking. IT Pro TV will keep you awake with their amazing training. Even when you're super tired, you can't focus, and you may have a flight the next morning that you're super late for because you're trying to get a NAS ready, they've got you if you're ever in that situation, like me. And if you're getting ready for that exam, to get that certification, to get that job, they do have practice exams and labs to cement those ideas into your brain. So if you want to learn IT like me, check out IT Pro by ACI Learning. I got a link below. And if you use my link, you'll get 30% off forever. It's a no-brainer. Just check it out. And now, let's do this. Now, just so you know, Casa OS is what this thing ships with. It's based on Debian. It's essentially just like a pretty wrapper on top of Debian 11, and it helps you install a bunch of apps which seem to be mostly Docker-based. Now, I could just make that work, but come on, Proxmox on something this tiny. Let me get this thing off. I feel like it's gonna put me in the app. On something this tiny that I can take with me anywhere? Pfft, come on. So I installed Proxmox on my Zima board. I installed it to an external SSD, and honestly, installing it is like installing it anywhere. You put the image on a USB drive, I booted to the USB on my Zima board, and just did the thing. Now, I will say this. One thing I wanted to have enabled was PCI pass-through, which Proxmox 8 does enable, because I want to be able to pass through my PCI devices. But you have to enable this, the IO, MMU, and VTD, and all that stuff in the BIOS before you install Proxmox. So I installed it initially, never worked. I re-enabled it in BIOS, then I reinstalled it after I enabled the settings in BIOS. Bam, PCI worked. So Proxmox is installed. Let me get logged in. It's just crazy to me. You can install it on such a small device. Bam, I'm in. So now I have my 2 goals, right? I wanted to have a router, and I wanted to have a NAS. Now you might be thinking, Chuck, why do you need a travel NAS and travel router? Well, if you missed my previous video, the travel router is meant to make things easier for me and my family. Wherever we go, whether it's hotel Wi-Fi, Airbnb Wi-Fi, or plane Wi-Fi, all I have to do is connect one device, my travel router. It grabs the Wi-Fi or Ethernet connection from wherever I am. It then takes that connection, broadcasts its own Wi-Fi to my family, offering them all that sweet, sweet internet.
Sweet, sweet
Internet.
I always hated it.
Saves me time in 2 ways. When we get to an Airbnb or wherever, I only have to connect one device to the Wi-Fi. Time saving there. And then all my family's devices are already configured to connect to my existing Wi-Fi, instantly giving them internet. Also, I can have that same device configured to automatically connect to VPN, protecting and encrypting all of our traffic. And it has the added benefit of me being in Japan, maybe wanting to watch some US shows or engage in some US-based content. I can be there while not being there. Very cool. The Travel NAS, I need that sucker to run Plex. I gotta have those TV shows on the plane for all my kids. I don't know if the plane's gonna have Bluey in their little cinema system. I gotta have that myself. 14-hour flight with kids, ages 1 to 12. This is what I need. Also, I'm gonna be recording this entire adventure because I wanna capture this. Taking my whole family to Japan, that's crazy. So I wanna capture that craziness, upload that footage to my NAS that's with me, and overnight, that sucker can just upload my footage to the cloud and get it back here to my studio where my editors can edit that. That's the idea. I decided to tackle the router part first because I thought it might be the hardest. I could run pfSense, but you look anywhere, people say do not run pfSense with wireless capabilities. Just don't do it. It wasn't meant for that. It was an afterthought. pfSense is great. Is it still great though? I ignored all the drama. I don't deal with that. So pfSense was out, so I'm thinking, okay, I installed OpenWRT on my Raspberry Pi. Can I install it on the Zima board? Zima board. I'm gonna call it Zima board because I used to love Zimas. Did Zima make a comeback? Now officially you can install OpenWRT, bam, directly on this. Software to hardware, right? But I wanted to install a virtualized image, which is not easy to do. But I did find this great article from this guy and a video of how to install it. I did get it up and running, but getting the drivers to work for anything was virtually impossible. At least for the time I had. I'm sure if I tinkered with it a bit, I could get it to work. But in the hour or so I tried, getting a USB adapter to work, getting PCIe to work, getting my Wi-Fi 6 antennas to work, it just didn't pan out. So I abandoned OpenWRT, and then I found this other thing called RASP AP. This is a project that does a lot of what OpenWRT does, but you can install it on any OS, whether it's a Raspberry Pi or just a Debian machine running on Proxmox on your Zima board. So I tried that. This actually started to work. I struggled with PCIe pass-through, but I did get a USB antenna to work. And this is kind of amazing. I'm running a wireless router inside a virtual machine on a Zima board on Proxmox. Like that's just cool, right? And I was about ready to say, yes, let's do it. But upon testing, I kept losing connection. And when I would lose connection on my phone, it wouldn't reconnect again. Now again, I'm sure if I troubleshooted this enough, I would figure it out. I don't have time. I gotta have something that works now. Now at this point, I felt kinda done. My dreams of having a travel router and NAS on one device running virtualized on Proxmox were dead, and I felt dead. So with no more time, I looked elsewhere for the router portion. How do I turn this thing into a router while also having it function as a NAS and whatever else I needed to? Given time, I could have made RASP AP work because I think it was just using DNS mask and host APD, just had a pretty wrapper to it. But then I found this guy. I forgot about him. This little guy, you've probably seen these before, maybe. It's a little device from GL iNet. It's a gigabit travel router. It's meant for travel. I mean, first of all, just look how cute this thing is. This is purpose built for exactly what I'm trying to do. A lightweight travel router that can give my family access to Wi-Fi without reconnecting all their devices and making it secure, while also tethering it to my resources to give them access as well. It's running OpenWRT and it has a pretty wrapper on top of it. Now, if you watch my travel router for the Raspberry Pi, OpenWRT is not for the faint of heart, getting it set up. This thing, it's stupid easy. You turn it on, you select what Wi-Fi network you want to connect to, and you choose what Wi-Fi network you want to broadcast. Click, 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 it's done. That's what I need on a trip where I'm taking my family to Japan. Something easy and stupid, so when I'm like half awake, coffee deprived, maybe. Do they have a lot of coffee in Japan? Please tell me they do. Then I can just easily figure this out while my kids are screaming. Bluey, Bluey, Bluey. Do your kids watch Bluey? So I thought, okay, that's not too big, right? I mean, I can somehow figure out how to 3D print these together into one nice package. So bam, my router solution is solved. So I'm back to Travel NAS. What do I do with this? I could go back to Proxmox and figure that out, but then I saw a fellow YouTuber, Nova Spirit Tech, talk about installing TrueNAS on his Zima board. TrueNAS. That sounds interesting because first of all, it's a NAS software or a NAS OS. Now I've never played with TrueNAS, so automatically I'm like, okay, I'm already doing something new here. Let's install a new OS I never encountered before and see what it's like. TrueNAS is awesome. Getting it installed is straightforward, like any other OS on any device you've ever installed. Flash the OS to your USB drive, boot to the USB drive, and install it. Now for my NAS, I do have two 2TB SSDs that I'm plugging in via SATA. There's a nice little Y connector that just plugs in both in, giving it power from one port. Pretty sick. Now again, I'm new to TrueNAS, but it wasn't too bad figuring out how to set up a quick storage cluster and get some things rolling. Well, actually, it kind of did take a minute because TrueNAS is a whole thing. And this was my first time using it, and I didn't have a lot of time to mess with it, tinker with it, learn it. But hey, I did get the storage set up. This was pretty easy, relatively easy, with a bunch of Google searches. I fumbled my way through it. But you know what tripped me up? Trying to set up Plex. Yes, you can install a ton of different apps on TrueNAS, Plex being one of them. And it's pretty cool. It actually installs with Kubernetes, which I love. But man, did the permissions just kill me. I didn't know TrueNAS permissions. I kept changing things, trying to get it to work, and I'm just like, you know what? I'm done. Let's blow that sucker wide open. Allow everything, everyone. Come on, people, come and hack me. That was my attitude at that point. I didn't care. And that's what I did. And sure enough, when you open everything and allow everyone, usually what you want to get in, gets in. So Plex now had access to the libraries where I uploaded the movies and TV shows. So we're good. Which, by the way, when you're in a rush and you're just trying to get things to work, that's how most hacks happen. In those moments. Always plan and slow down, except when you're about to get on the plane to Japan. Then just go crazy. So anyways, yeah, I uploaded the movie, tested that. So cool. I uploaded some Bluey because I had to make sure my kids could test that and work with that. So I uploaded Bluey and actually decided to do a test with them. So I loaded up my NAS, went to the house, and set about doing my experiment.
All right, guys, I need y'all to test and see if Bluey works, okay?
It's not working.
What? Okay, it's 11:54, almost midnight. I'm leaving for Japan very soon. TrueNAS failed me. I thought it was great. I was so confident and happy about it. I bundled it up and took it to my house to test it with my daughters. I booted up and Plex never comes up. It just doesn't come up. I log into it and look, it's the dumbest thing. So Kubernetes, when it's deploying Plex, it's pulling the newest image from GitHub every time. And when it can't reach GitHub to pull that image or just at least make sure it's the latest, it won't boot. It just says, oh, I can't reach GitHub, I'm sorry. Now, could I figure out how to make that work? Maybe, but not in this state. Not this close to the finish line here, no. So back to the drawing board. And I ended up going back to Casa OS. The OS I was sleeping on actually is pretty cool. It took me a bit to get things rolling, but I got it. I'll detail all that stuff here later because I can't tell you about this right now. I've got to get it set up. I got to go to Japan. I'll tell you when I get to Japan. How about that? Okay, I'm back from Japan. Let me tell you about Casa OS. Casa OS, the OS that ships with ZimaBoard, and the one I started with, is what I ended up with. Now honestly, I'm kind of bummed about this because I wanted to do something cool and crazy. Nothing default, but I ran out of time. And I was about to drop the entire project altogether. Who needs a NAS? I'll just wing it. But I thought, you know what? Let me try one more Hail Mary. Let's try Casa OS, the thing it came with. Let's see what it can do. I was kind of surprised. So I re-imaged it back on there. Didn't take too much. And here it is. It's got a beautiful web interface I can just access over the network, which is super handy. So when I got to an Airbnb or even the plane, I just plugged it in, waited for it to boot up, and I would log into it. Again, this is just a pretty wrapper on top of Debian 11. Now right off the bat, you can see I was doing some fun stuff. But before we jump there, let's talk about storage. The main thing I needed it for, I needed that NAS. Well, here it is right here. Let's jump in there. This was plug and play. I had my 2 SSD drives plugged in via SATA, and they just were here. They were recognized. So I labeled them. The only downside is I couldn't combine them into one. They did have a beta thing that I could do to merge the storage. I wasn't about to play with beta on a trip where I wasn't gonna do that, no. So I just made one hard drive my Plex and one hard drive my NAS. I say hard drive, my SSD. And then really most of what I did was just access the file app right here in the browser. Jumping into my NAS, I would just have a folder for each day of footage I recorded. And we recorded a lot. And getting the footage on there was super simple. All I would do is have this external hard drive, load up my footage on there, and then connect this to the ZimaBoard. So watch, I'll plug it in right now. You should show up here in a second. Yep, there it is. So cool, that solves one problem. I'm getting all my footage to this NAS. But now, how does that NAS get my footage to my studio here? Normally, when I use something like Synology and then TrueNAS, I would have synced all my footage to Google Drive, and Google Drive would then sync down to my studio. I didn't see a quick way to do that, but I found something even better. It's kind of amazing, actually. Check this out. Now, just so you know, Casa OS has an app store. Clicking on that will take us to it, I think. And they have a bunch of stuff. And this is where I simply downloaded and installed SyncThing, which will run as a Docker container. And this might be my go-to for all syncing. Let me launch it real quick. It'll open up its own web interface. And how this thing works is simple. First, I'll define the folder that I want to sync, which is this guy right here. Let's just go Japan. Keeping in mind this is sync thing running on my travel NAS. Then I log into my NAS here at my studio. And on this NAS, I ran sync thing as a Docker container. And you can actually see that here as a remote device. And how you do this is so simple. All I had to do is click on add a remote device here. And I would just put in the device ID and then name it something I wanted to and then click on save. And the device ID would be found under actions and show ID. And just by adding that remote device with that device ID, they magically over the internet found each other. No VPN, and they started syncing. Of course, I had to find some folders and some syncing rules. Like for my use case, I only wanted to send data. I didn't want it to sync back and forth. But this just stinking worked. And no matter where I went in Japan, they connected up, they found each other, and they started syncing. And it was pretty fast, assuming my internet connection was fast. Sometimes it was not. But leaving this thing up and letting it trickle, upload overnight, over time, was pretty great. So if you need a way to sync two remote places, sync thing is pretty amazing. And then finally for Plex, this was pretty simple. You saw that I had my files here and I had Plex, my Plex SSD, simply had two folders, movies, TV shows, all the essentials. And then going through the App Store, I just installed Plex. And this was simple. And accessing my Plex system, I could watch any show. Bluey kind of saved our lives a little bit while in Japan. But this worked like a charm. And as we traveled throughout Japan and we had all of our kids with their iPads, they could simply connect back up to our NAS, watch all their stuff. And yes, this did work on the plane. I just put this device under my seat, plugged it in. Felt kind of weird because I'm like, you gotta wonder what people are thinking about me. Like, what's this guy doing? What's this device he's putting under the seat? And what's he plugging in? I had those thoughts. I ignored them because it was a 14-hour flight. But it worked. And we did this everywhere, on trains, and hotels, Airbnbs. And real quick, let me give you a clear example of our diagram, our network diagram as we traveled. So we have our Zima board here. Just gonna make it a square. He had two SSDs connected to his SATA ports with the SATA Y connector, which is pretty cool. And he was hardwired in, and I had an Ethernet cable plugged in from him to my little travel router, my GLI.net travel router. I'll give him his antennas here. Now this router was doing a few very important things. First, he's being a router, he's being himself. He was in charge of DHCP. I had a DHCP reservation for Mr. Zima board down here, 10.19.7.19, that's what I had. And he was also broadcasting a wireless network called Let's Just Go Fam that we would connect to, all our devices. Now a fun little thing here for DNS, I was actually using Pi-hole running as a Docker container on the Zima board, which you can see right here, let me show you. Pi-hole was definitely one of the apps that were running. Let me get logged in. And here it is, my activity over, let's see, long-term data, graphics, all time. And there's all my time using it. It's kind of fun to watch. A lot of requests. I also ran Uptime Kuma, a little thing called Smoke Ping, which would tell me how healthy the internet connection was wherever I was. I was geeking out, it was pretty fun. But anyways, back to our diagram. The key thing was the internet. And wherever we go, what I look for first is a hardwire. Where is the router in this Airbnb that I could hardwire my router into? Thankfully, a lot of Airbnbs just had it sitting out. I would hardwire myself in, bam, I've got extremely fast internet. Other times, I would have to use the built-in client mode for the router, the GLI.net, to connect to whatever wireless they offered. That's my wireless, I don't know why it looks like that. But seriously, this worked like a charm as I traveled throughout Japan. We went everywhere, and it served us well. I'm proud of this little device. That's all I got. I'll catch you guys next time.
In mid-January 2024, the semiconductor EDA giant Synopsys announced the acquisition of the software firm Ansys for $35 billion. Ansys produces software for computer-aided engineering, or CAE. They have a fascinating history. But why buy it? There's a trend going on here, and it involves this new sexy technical trend of the day, chiplets. In this rather wide-spanning video, we look at the intersection of design and computer simulation. But first, I want to remind you that this video is brought to you by the Asianometry Patreon. Early access members get to see new videos first and selected references for those videos. Early access really helps me a lot, and I appreciate every pledge. Thanks, and on with the show. In the 1960s, John Swanson was working at the Westinghouse Astronuclear Lab in Pittsburgh. He went there to work on nuclear-fueled rockets with the goal of going to Mars, the Nerva nuclear rockets. His work involved doing stress analysis on various components. To do this, Swanson had to model how a structure might function under a particular load. However, trying to mathematically model a big, complicated design was challenging. But if you divide that structure down into smaller pieces, those smaller pieces are easier to predict. Tie those pieces together, and you get a far better idea of how the larger structure will act. This is what we now call finite element analysis, or FEA. In FEA, we break something like a car design down into millions of little shapes and use that to predict how that car design might react if it hits a wall. In those days, the FEA equations had to be worked out by hand using desk calculators, which was long, complicated, and error-prone. So Swanson learned how to code and wrote a few programs to do this FEA. By the late 1960s, it became clear that the nuclear rocket was not going to Mars. So Swanson left, moved back in with his parents, and founded the company Swanson Analysis Systems to develop the ANSYS simulation software suite. Westinghouse brought Swanson back as a consultant, which helped Swanson keep food on the table while he coded up ANSYS on a time-shared mainframe owned by US Steel. ANSYS, Swanson went with the name because the lawyers said it didn't violate anyone's trademark, was finished in 1970, and Westinghouse was the first user. Over time, Swanson and his small team ported the software to mini-computers like the VAX and added crucial features. In 1994, Swanson sold majority control of his company, which had annual revenues of about $30 million, to the private equity firm TA Associates and stepped down. They took the company public 2 years later, changing its name to that of the flagship product. Swanson retired soon after that and has since focused on philanthropy. ANSYS's FEA tools have since evolved to embrace a variety of CAE subcategories. Broadly speaking, CAE is about using sophisticated algorithms to simulate, validate, and solve problems in engineering projects. The name is similar to computer-aided design, or CAD, but they're not the same. CAD is for producing the design, while CAE is for testing how that design performs under certain conditions. This is helpful because engineers can now diagnose and troubleshoot problems in a design without having to do as much real-world testing. Since it can cost millions of dollars to build a modern plane or car prototype, and certain conditions cannot be easily replicated in a wind tunnel, this saves a lot of time and money. The rise of more powerful computers, including those within the cloud, has made it more feasible for users to simulate increasingly complicated designs inside a computer. FAE is pretty interesting, and it would be fun to use it to simulate what happens when an integrated circuit hits a brick wall at relativistic speeds, but in a semiconductor industrial context, we want to look at a different major CAE subcategory, computational fluid dynamics, or CFD. CFD programs help solve the complicated nonlinear equations that govern the motion of fluids. Brace yourself for some mind-blowing stuff, but fluids are not like solids. Fluids like air or water react to shear stresses differently than solids because their shapes deform without losing volume, so these fluid dynamics equations are extremely intense. Any calculator, human or otherwise, must simultaneously maintain multiple factors like conservation of mass and momentum in many directions. CFD applies to all sorts of real-world engineering situations, but is particularly big in heat transfer analysis. Engineers can use it to track heat sources in a structure, how that heat conducts or radiates throughout, and how we can carry away that heat using a fluid like air. Considering this, we have long sought ways to model these fluid movements. In 1922, the English scientist and mathematician Lewis Fry Richardson published the book Weather Prediction by Numerical Process. It radically proposed a set of differential equations for predicting the weather. His book also fantasized about the possibility of a, quote, forecast factory, end quote. In it, you would have many dozens of, quote unquote, computers, human computers in this case, calculating these equations for different parts of a world map. This, of course, was a fantasy, but fun nevertheless. By 1940, the available analytical models for modeling fluid dynamics were fragmented and in disarray. Existing models based on older principles proposed by the mathematicians Leonard Euler and Lagrange were elegant, but did not match up with what was happening in reality. This situation changed thanks to the urgency of war. In the waning years of the Manhattan Project, it became crucial for the Americans to track the behavior of shock waves and how they propagated through things. research continued after the war ended and hydrogen bomb development began. In 1950, Robert Richtmyer and John von Neumann published a paper introducing the concept of, quote, artificial viscosity, end quote. This simplified the equations for computers while maintaining fidelity to the basic physics. Over the decade after that, a team at Los Alamos led by Frank Harlow contributed several foundational CFD algorithms like particle in cell or fluid in cell. These works together enabled the foundations of CFD as we know it today. Professor John Chu of Columbia coined the term in 1967, in addition to contributing crucial differential equations for the discipline. CFD programs have since evolved to reproduce and visualize all kinds of thermal dynamics. This is helpful for air conditioning systems, vents, and, interestingly enough, semiconductors. In previous videos, I've talked a bit about the growing trend in advanced packaging. One of the major examples of this is AMD's flagship AI accelerator chip, the MI300. This chip has been built up to be some kind of an NVIDIA slayer amongst AMD enthusiasts, but whatever you might think about AMD and NVIDIA, it is a magnificent piece of silicon engineering. I quote Dylan from Semi-Analysis here, "The MI300 is the most incredible form of advanced packaging in the world. Over 100 pieces of silicon stuck together in 3 layers on top of an interposer, which is kind of like a PCB for silicon chips. These silicon pieces are connected using through silicon vias, which are holes drilled into the die. We can then run copper interconnects through these vias. Advanced packaging techniques like these allow us to produce larger, more powerful pieces of silicon without majorly hurting yields. Certain compute chiplets can be made using advanced nodes, while other, less advanced stuff like I/O can be done in trailing edge fabs." One of the big issues, however, with these vertically stacked semiconductor packages and others like it is heat. Chips generate heat. In a traditional 2D monolithic IC, we know how to deal with this heat. All of the silicon pieces are accessible, so heat generated by the chip can be dissipated out either through the silicon substrate on the bottom or the heat sink on the top. But when you stack more than maybe 2 pieces of silicon together, we can't just throw a big ol' heat sink on top and call it a day. That is because we no longer have access to all of the chips. When you consider that the silicon pieces do not all have the same heat profiles and that heat cannot travel very far, then you end up with local hotspots. These higher temperatures hurt the chip's performance and overall lifetime. I'm compelled to inform you of the fable of the Asian giant hornet. If it ventures too deep into a Japanese beehive, the bees tightly surround the hornet and beat their wings to high temperatures. The poor hornet, which only wants to eat, is cooked to death. Likewise, for an advanced packaged IC, heat from silicon operations or beating bee wings can compromise performance. It can fatigue the soldered interconnects, warp the silicon substrate, or even crack the die entirely. Considering the consequences, it is important that chip designers build structures into their stacked packages to deal with this. The industry has tried several things. There's a whole part of the industry dedicated to heat control. We have silicon or software level measures to take. For instance, writing code to limit the chip's performance so that we don't overheat the package. There are also packaging level things we can do, like immersing the whole chip in a heat dispersing fluid, or even creating silicon fins sticking out from the interposers to shuttle away the heat. There's a strong focus on adapting existing technologies to minimize risk of failure. One example is the solder ball interface between the dies. Changing the filling in between the balls can greatly improve the heat distribution profile of the stack. Regardless of the methodologies employed to deal with the heat, we're going to want to simulate it out to see if it works. A wafer takes about 3 to 5 months to produce, and that does not include packaging. So it could take months to get a complete package to measure, test, and validate its heat profile. But we don't have that much time to wait. Advanced chip design takes far too long as it is. So being able to simulate the thermal profiles of a particular stack design inside a computer without needing to go and build a prototype to test in real life is hugely beneficial. That means CFD. For instance, calculating heat transfers from between 2 components within a package requires us to know the local fluid temperature, as in the temperature of the parts in contact. But as we established earlier, CFD is extremely difficult to model due to the complicated interplay of various factors. Such programs need to produce accurate results that match within real-world experimentation while also being intuitive to use, since designers are often time-pressured. For this reason, CFD programs for thermal simulations of electronic packages are very mature, around for over 20 years. So, semiconductor tool and IP ecosystem providers like TSMC prefer to partner with existing CFD makers like ANSYS rather than make their own. In 2021, ANSYS announced a partnership with TSMC to deliver a thermal analysis solution for 3D Fabric. 3D Fabric is TSMC's umbrella of advanced packaging technologies. Import a package from an EDA software and you can run electrical, thermal, and structural simulations on it. Getting this stamp of approval, as well as others from the world's biggest foundry, is a compelling sign of ANSYS's growing presence in semiconductor design. It does make me wonder, though, if we should allow Synopsys to actually buy them. On the surface, the businesses seem quite separate, but ANSYS is growing in the industry, and semiconductor design and simulation are soon to collide, especially as generative AI makes its way into the design flow down the line. Simulations can be a way to validate those designs, like how we use a Python runtime to validate ChatGPT's written code. Just a random thought. Maybe I'm crazy. One more thing. I do think that's a random thought. Maybe I'm crazy. One more thing. I do just designs, like how we use a Python runtime to validate ChatGPT's written code. Just a random thought. Maybe I'm crazy. One more thing. I do think that Synopsys being willing to pay $35 billion does say that heterogeneous integration, i.e. the chiplet approach, is here to stay. Expensive AI chips like the MI300 are only the beginning, the leading edge of the sword. I get the feeling that we are going to be seeing the MI300's approach trickle out to almost every part of the semiconductor space, except maybe the smartphone. Considering all the trailing edge semiconductor fab capacity being built around the world right now, users will want to mix and match process nodes and then slap it all together with advanced packaging. This means more complex advanced packages down the line, and that is going to present a lot of challenges because heat isn't the only major thing for packaging designers to overcome. Another one that comes to mind, for instance, is capacitance, which arguably might be harder. This all in turn incentivizes us to produce better tools for designing and manufacturing such advanced package designs. Synopsys is setting out on that journey and putting down $35 billion to back it. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.
KSI is one of the world's most popular YouTubers, but yesterday he accidentally exposed the pump and dump crypto scams that he promoted. They've been hidden for 2 years, but only came out when KSI logged back into his old Twitter account, saying, "Does this still work?" Now, if you didn't know, this is KSI's crypto account where he used to talk about crypto coins he liked. But he messed up because one investigator has been waiting for him to return to the scene of the crime. And that person is not me. It's Zach XBT, a crypto investigator on Twitter who I'll link below because his work is incredible. He's a friend of the show. We've collaborated a lot. I just encourage you to go follow him. But I was shocked when he said this. In before he starts sharing garbage again, dumping your tokens on Logan Paul's lapdog is permitted and encouraged. Now, many people, including myself, hadn't seen anything from KSI to this point that seemed shady. But Zach had been waiting for this moment. He goes on, "Remember when KSI posted this? All of a sudden, my XCAD bag is looking juicy again. HODL gang then proceeded to dump $850,000 worth of XCAD over the following days from his wallet address." Now, obviously, I was stunned by this. But looking at the date of when this all happened, I realized Zach has been holding onto this piece of evidence, waiting for KSI to come back to this account for years. He had this tweet in the drafts, and KSI logging back in activated the trap card. Zach also shared a picture as proof, a series of transactions from KSI's wallet, where starting on March 27th, when he sent that tweet, KSI started selling XCAD. The same day he tweeted he was part of the HODL gang, slang for someone who wouldn't sell this crypto coin, right? In fact, that wasn't the only time KSI has mentioned this holding stance publicly.
I'm holding my bags. I'm holding my Luna, my XCAD.
Videos like this are why people genuinely thought KSI was just buying and holding, but he wasn't. This time he sold. And he tweeted again on March 30th, 2022. Me looking at ZIL and XCAD right now. And it might look like that means he's excited about this. But really, he was looking at the sell button because he continued to sell XCAD to his fans who thought he was part of the HODL gang once again. And this is what I mean by a pump and dump scam. He got his followers excited while selling his own crypto bag at the same time. In total, over $800,000 was sold by KSI over a few days and these two tweets, according to ZachXBT. Now, as a quick aside, if you're wondering or skeptical of the fact that influencer tweets can have any kind of effect on a token price or volume, I whipped up a chart for you showing volume of XCAD during the days when KSI tweeted. You can see that trading volume spiked millions of dollars on those days, which in part were some of his followers putting money in as he sold. Today, the price of XCAD has plummeted from $3 to about $1. Now, as always, with such large allegations, I wanted to be sure to reach out to KSI to give him a chance to explain these large accusations. After all, I didn't find this, Zach did. So I reached out to KSI over Twitter, and he gave me the following statement. Hey bro, I'm still HODL gang, LMAO. Sold some profit, as well as my own money, to put into Luna, thinking I would profit more to buy back more XCAD, and took a major L. Still fully believe in XCAD, the ability to earn from watching content. Honestly, you should talk to Redacted. He's very excited about this project. I never left crypto. I've just been watching it from the shadows. It's kind of hard to leave when you've invested so many years into it. So that's his statement. He then shared a personal account screenshot showing that he does have some XCAD still held. But while that's an interesting fact and an interesting explanation, it doesn't really change the core accusation of whether he pumped and dumped his fans. And I thought it was interesting KSI didn't deny the crypto wallet was his, or that he made that amount of money. He's just telling us, well, I'm still hodling some of it, just 800,000 of it I sold. Now, to be honest, I don't buy this explanation for a second. But I kind of was feeling like I had to leave the story there. It felt like a one-off scam that I talk about on my new side channel, CoffeeZilla Extras, but the story would die there. But then I got another message, which changed everything from Zach. He said, I have one more KSI example with a different coin. Turns out on March 20th, 2021, KSI tweeted this. 2 NFT coins I'm very bullish on, Super and Earn. Any other NFTs I should look at? Now, normally when you're bullish on a coin, you buy that coin. But that's not what KSI did. See, right after he tweeted that, 6 hours later, he sold $174,000 worth of Earn token. And then 4 hours later, sells another $174,000. Now, if that isn't a textbook pump and dump, I don't know what is. He tweeted, that's the pump. Within 24 hours, he sells $348,000. That's the dump. It couldn't be more clear. Or so I thought, because I asked KSI about this, and that's where things got a bit muddy. He says, I don't really remember the details of every transaction I made. These were coins I put my own money in, thinking they would do well. I would listen to what people said on Twitter and just follow stuff. I invested in Doge, etc. I didn't have malicious intent in trying to scam. I was new to crypto, so I was excited, putting money in random things and trying to chase the pumps, and ultimately lost heavily. I hope people didn't take advice or tweets as gold, because looking back at my track record, I was effing dog shit. I wish I was an evil genius that would pump and dump at the right time, because then at least people would say that I had some wit about me. Reality is, I was just shit at crypto. And that's basically KSI's defense. He was dumb, he was bad at crypto, but is that true? Well, he says he put in $2 million of his own money and lost it all in the end. He says, quote, I made zero profit on crypto. In the end, I lost it all on Luna. Look, I haven't seen his accounts. Maybe that's true. Either way, even if he is bad or dumb with crypto, it doesn't explain the pump and dumps. Like, telling people you're bullish and then selling is not explained by, I was new, I was dumb. And I said as much. I said, I'm just trying to understand why you traded the opposite way that you were saying on Twitter. And KSI replied this, because I thought I was getting trolled. Honestly, every time I tweeted something, the opposite would happen on the market. So I decided to tweet the opposite of what I was actually doing and still took an L. So just to be clear, KSI's story that he's going with is that he thought the market was against him, so he publicly said one thing while privately, secretly doing the opposite, which is kind of the definition of a pump and dump when you promote that to a big audience. You say you're gonna buy to your followers while secretly selling. Whether or not it's a successful pump and dump, whatever pump and dump, that's what it is. Now look, I understand that people are gonna have conflicting ideas of whether this was malicious or not, and I think it's gonna entirely depend on whether you think KSI's story makes sense. I'm just trying to provide full context, while also giving you my opinion on that, which is that I don't really buy that he had no clue that tweeting one thing would positively affect the price in his favor. Meanwhile though, while I was confronting KSI, I heard a final response from Zach XBT, which I think moved the needle a bit. He said, I found another example. See, on May 11, 2021, KSI Crypto tweeted, "This is about to explode." Only moments later though, he sold $25,000. Didn't buy it, which I get it. It's a relatively small amount, but it furthers that same pattern of behavior. It's just a matter of what you think that behavior was. If you ask me, I think KSI tried to use his influence to move the market for himself in crypto through a few pump and dumps. He may have lost all his money eventually in a Ponzi scheme, but that does not make what he did okay. In fact, I think it's fair to say that a lot of his followers, we saw that, he influenced millions of dollars in trading volume, went into some coins that are now doing very poorly. But ultimately, I think the true piece of cosmic irony for KSI here, though, is that he would have gotten away with all of this. No one would have known about any of it if he just hadn't logged back into Twitter for one last spin at the slot machine.
It seems like every trash bag brand claims to be the best or the strongest, but in reality, they all seem to break open and spill everything out onto the floor. So the question is, which brand is the best? We'll compare the trash bags for drawstring and trash bag strength. Then we'll see which bag has the most tear resistance and which bags offer the best grip on the top of the trash can. At a price of $28 for 250 bags, or only 11 cents each, the least expensive brand we'll be testing is made by Rely. All the bags we'll be testing have a 13-gallon capacity. It claims to be tear resistant and leak proof. We're going to test that. The Rely brand does a good job of positioning the next bag for easy access. Double thick top multiplies the strength of the top 5 inches of the bag. It's designed this way to prevent finger punctures of the bag during removal. There's no information on the packaging regarding where the bags are made, and the Rely trash bag weighs 13.15 grams. In the first test, let's compare the strength of the drawstrings and bags. I'll first place a piece of metal that's wrapped in a towel inside each trash bag. The towel will prevent any sharp edges from cutting the bags, and the top of the bag tore away from the Rely bag at 37 pounds. Let's see how much force the bag can handle. And the Rely bag gave up at 48 pounds. At a price of $30 for 200 bags, or 15 cents each, is this Neat brand. Is recycled plastic any good? We're about to find out, since these bags include 50% recycled material. The Neat brand also does a great job of positioning the next bag. These bags are triple ply fortified using Harmonix advanced film technology. They claim this technology makes them resistant to puncture, tears, and leaks. The Neat brand is made in USA, and it's 25.45 grams for the Neat brand. And the Neat bag's drawstring gave up very early at only 23 pounds. However, the bag held in there longer than the Rely bag, finally blowing out at 62 pounds. At a price of $17 for 110 bags, or 15 cents each, is this T4ing brand. The T4ing bag has to be torn away from the roll. They claim that their bags are leak-proof and tear-resistant. The T4ing trash bags are made in China, and the T4ing bags are right at 13 grams. And the T4ing bag is a lot less stretchy, and it made 73 pounds without blowing out. However, the bag is going to fail pretty quickly if there's any sort of damage. So it's going to be very interesting to see how it holds up with some pointed objects in the bag. At a price of $19 $22 for 120 bags, or 16 cents each, is this Amazon Basics brand. And the Amazon Basics is designed for easy access. Amazon Basics has about 90,000 sales of this bag every month. It'll be interesting to see how they perform against the competition. The Amazon Basics is made in USA, and it's 23.76 grams for the Amazon Basics. And the Amazon Basics drawstring performed very well at 56 pounds to move into the lead. And the bag also performed well, finally blowing out at 57 pounds. At a price of $32 for 200 bags, or 16 cents each, is this Kirkland brand, which is sold at Costco. They claim that their FlexTech plastic expands to hold more. And the Kirkland box is set up to dispense bags nicely. They claim flexible strength, leak protection side seams, tear-resistant technology. The Kirkland trash bags are made in USA, and it's 23.29 grams for the Kirkland. And the Kirkland drawstring performed well at 48 pounds to move into second place behind the Amazon Basics. And the Kirkland bag performed almost the same as the Amazon Basics, finally blowing out at 56 pounds. At a price of $15 for 80 bags, or 19 cents each, is this Hefty Ultra Strong. This is a very popular bag with 80,000 sales a month, and the Hefty brand does a great job of dispensing bags. Hefty claims these bags stretch to expand and accommodate oversized loads without punctures, leaks, or tears. The Hefty trash bags are made in USA, and it's 21.92 grams for the Hefty. And the Hefty bag wasn't quite as hefty as the Amazon Basics or Kirkland at only 36 pounds of drawstring strength. And the bag also blew out much sooner than the other brands at 38 pounds. At a price of $14 for 70 bags, or 20 cents each, is this Full Circle brand. And the Full Circle bag has to be torn away from the roll. Full Circle claims that these bags are biodegradable, made from 80% recycled plastics. The Full Circle is made in USA, and the Full Circle bag weighs 14.32 grams. And the Full Circle trash bag does not have a drawstring. And the Full Circle is very stretchy and finally gave out at 50 pounds. At a price of $27 for 120 bags, or 23 cents each, is this Commander brand. Commander claims that you do not have to worry about leaks or spills. The Commander does a great job of dispensing bags. Same value as the big brands at half the price. The Commander bags are made in USA, and the Commander weighs 18.83 grams. And the Commander's drawstring gave up much sooner than most of the other brands at 32 pounds. And the Commander trash bag blew out at 58 pounds. At a price of $14 for 60 bags, or 23 cents each, is this Eco brand. And the Eco bag seems inconsistent with dispensing the bags. It claims to offer sensible eco living. They claim that their trash bags are 10% stronger than leading national trash bags. And the Eco bags are made in China. And it's 24.95 grams for the Eco. And the drawstring on the Eco performed a little bit better than the Commander at 34 pounds. And the Eco is a lot less stretchy, and that really helped it with strength at 74 pounds. At a price of $33 for 140 bags, or 24 cents each, is this HDX brand, which is sold at Home Depot. The HDX seems well designed for dispensing bags. They claim that they have a double thick top to add strength where it's needed most. The expandable drawstring feature allows the top of the bag to comfortably grip the trash can. We're gonna test that. And the HDX brand is made in USA, and is 21.37 grams for the HDX. And the HDX trash bag came up 1 pound short of the Kirkland trash bag at 47 pounds. And a super stretchy HDX bag performed well at 64 pounds before giving up. At a price of $25 for 100 bags, or 25 cents each, is this Perk brand. The Perk bags are designed to fight the funk, and the Perk did a pretty good job of making easy access for the next bag. The Perk bags are made in USA, and it's 22.8 grams for the Perk. And the Perk's drawstrings broke at 42 pounds, or 5 pounds less than the HDX. And the super stretchy Perk must have doubled in length before finally lifting the weight off the ground and suddenly blowing out at 74 pounds. We'll be testing two different types of trash bags made by Glad. The first is the Glad Force Flex at a price of $34 for 120 bags, or 28 cents each. The Glad brand is well designed for dispensing bags. They claim to be made stronger with less plastic. The drawstring is supposed to grip so that the bag stays in place. The Glad trash bags are made in USA, and it's 16.77 grams for the Glad. And the drawstrings on the Glad just tied the Amazon Basics for first place at 56 pounds. And the bag made it to 65 pounds before finally giving up. At a price of $21 for 70 bags, or 30 cents each, is this Steel Coat brand. And the Steel Coat seems inconsistent with dispensing the bag. Diamond Flex stretch technology prevents rips and forms the trash inside. The Steel Coat is made in USA, and it's 20.42 grams for the Steel Coat. And the drawstrings on the Steel Coat gave up the earliest yet at only 19 pounds. And the Steel Coat bag just doesn't have much fight, blowing out at only 42 pounds. At a price of $60 for 200 bags, or 30 cents each, is this Ox Plastics brand. They claim that their bags are tear resistant, designed for household as well as commercial use. The Ox Plastics is made in USA, and the Ox weighs very close to 42.5 grams. And the Ox Plastic doesn't have a drawstring. And there's a reason why they call this bag the Ox. And the Ox weighs more than twice as much as most of the other bags, and it made very easy work of the 74-pound load. Even after making several tears in the bag, the Ox still lifted the load. At a price of $27 for 90 bags, bags are 30 cents each is this Hippo Sack brand, made from sugarcane materials instead of fossil fuel. The Hippo Sack bag has to be torn away from the roll. Guaranteed stronger than all leading brands. We're going to test that. They claim that the Hippo Sack is puncture and leak proof. The Hippo Sack bags are made in USA. And the Hippo Sack weighs 25.56 grams. And the plastic handles on the Hippo Sack gave out at 60 pounds. Apparently, hippos don't like to be outdone by oxes. And the Hippo Sack also lifted the 74 pounds of weight several times. At a price of $27 for 90 bags, or 30 cents each, is this Glad Force Flex Max. The Glad is well designed for dispensing bags. This is a very popular bag with 40,000 sold each month on Amazon. They claim that this bag is 25% more durable. The Glad trash bags are made in USA. And it's 18.87 grams for the Glad Max strength. And the Glad Max's drawstrings definitely did not outmax the competition at only 33 pounds. And the Glad Max bag performed very well for a lightweight bag, finally blowing out at 71 pounds. At a price of $5 for 13 bags, or 38 cents each, is this Tough Bros brand. Unfortunately, the bag is advertised as having a drawstring, and it doesn't have one. The Tough Bros is made in China. And the Tough Bros is the lightest yet at only 9.29 grams. And the Tough Bros bag is not very stretchy, and that really helped it on this test. And the Tough Bros was able to lift the 74 pounds. Adding a tear to the bag, and the Tough Bros finally gave up. And the most expensive bags we'll be testing at a price of $29 for only 40 bags, or 73 cents each, is made by Hold On. You have to tear away the bag from the roll with the Hold On brand. Made with unique combination of non-toxic plant-based ingredients. That includes PBAT, PLA, cornstarch, and more. Made in Austria. And the Hold On bag weighs 28.57 grams. And the drawstrings on the Hold On brand gave up the soonest yet at only 16 pounds. However, the bag did perform well, finally letting go at 60 pounds. When it comes to the strength of the drawstrings, the Amazon Basics and the Glad Force Flex came in on top at 56 pounds. The Kirkland trash bag and HDX also performed well at 48 and 47 pounds respectively. When it comes to bag strength, several of the brands were able to lift 74 pounds. Wrapping a towel around a sharp object to avoid damaging the plastic trash bag just isn't too realistic. So let's start off with 35 pounds of nuts and bolts to see how the bags hold up. And the Rely bag almost made it to 35 pounds, but it came up short at 32 pounds when it finally blew out. And the Neat bag lifted 35 pounds without a problem. So I'll go ahead and add more nuts and bolts. And the Neat bag performed very well at 68 pounds, or more than twice as much lifting force as the Rely bag. And the T4ing made it to 74 pounds with a towel wrapped around the metal. However, the bag gave up at only 55 pounds with the nuts and bolts. And the Amazon Basics made it to 56 pounds of soft weight. And the nuts and bolts really took a toll on the Amazon Basics at 44 pounds. And the Kirkland made it to 56 pounds of soft weight. And the Kirkland performed a little bit better than the Amazon Basics at 48 pounds. Unfortunately, this trash can blew out, but fortunately, I do have another trash can that we can work with. And the Hefty gave up at 38 pounds, lifting the soft weight. However, the Husky did a much better job lifting the nuts and bolts at 52 pounds since the nuts and bolts were more evenly distributed. And the Full Circle made it to 50 pounds with the metal wrapped in the towel. And the nuts and bolts weakened the Full Circle quite a bit, and it blew out at 35 pounds. And the Commander made it to 58 pounds with the soft weight. And the nuts and bolts took a small toll on the Commander, giving up 10 pounds, finally blowing out at 48 pounds. And the Eco made it to 74 pounds of soft weight in the previous test. And the Eco almost lifted the entire bag of nuts and bolts, but gave up at 70 pounds. And the HDX made it to 64 pounds of soft weight in the previous test. And the HDX gave up 9 pounds of strength with the nuts and bolts at 55 pounds. And the Perk lifted 74 pounds of soft weight without a problem. And the Perk lost 21 pounds of strength, giving up at 53 pounds. And the Glad made it to 65 pounds with metal wrapped in a towel. And the Glad gave up 15 pounds sooner with nuts and bolts, blowing out at 50 pounds. And the Steel Coat gave up early at 42 pounds with the soft weight. And the nuts and bolts applied a more even distribution of the weight, which helped the Steel Coat this time at 54 pounds. And the Ox lifted 74 pounds in the previous test. And this bag is called the Ox for a reason. And the Ox lifted all the nuts and bolts and refused to blow out. After bouncing the bag off the bottom of the trash can several times, the bag finally blew out. Very impressive. And the Hippo Sack also made very easy work of the 74 pounds of soft weight in the previous test. And the Hippo Sack also lifted 70 pounds of nuts and bolts. And the Hippo Sack gave up a little bit sooner than the Ox after a couple of bounces. And the Glad Max is a very lightweight and stretchy bag at just under 19 grams. And the Glad Max performed well for a lightweight bag, finally blowing out at 60 pounds. And the Tough Bros is trying to avoid this test. So I'll have to try this test again with a little bit of help from a bungee cord. This is an extremely thin and lightweight bag at under 10 grams. And the nuts and bolts destroyed the Tough Bros, and it gave up at 7 pounds. And the Hold On made it to 62 22 pounds with the metal wrapped in a towel. And the Hold On only gave up 9 pounds of performance with the nuts and bolts finally blowing out at 53 pounds. So the only 2 trash bags that lifted all the nuts and bolts includes the Ox and the Hippo Sack. However, the Eco and Neat also performed very well. And the top 4 brands are also the heaviest in the lineup. The Glad Max finished in 5th and performed extremely well considering that it's a much lighter bag at around 19 grams of weight. Most of the trash bags advertise their ability to resist leaks. So let's add 20 pounds of water to each trash bag to see which bags have been properly sealed and which ones are leakers. And it's been about 5 minutes. So let's see if the Rely bag is a leaker. And the Rely is a leaker, and the point of failure is at the worst possible location at the seam at the bottom of the trash bag. And the Neat trash bag weighs about twice as much as the Rely bag and is much better sealed. No water accumulation in the trash can. And the T4ing is a very lightweight bag at only 13 grams. And the T4ing bag did not leak enough in 5 minutes to create a puddle in the trash can, but it's definitely leaking. And the Amazon Basics bag weighs almost as much as a Neat bag. While there wasn't enough water accumulation in the trash can to create a puddle, the bag has a very small leak in the bottom seam, just like the Rely bag. And the Kirkland trash bag weighs very close to the same as the Amazon Basics. And the Kirkland trash bag is dry, and so is the bag. The trash bags have been on the concrete for several more minutes, and the T4ing is leaking badly. The Neat trash bag is still dry, and the Rely bag has a very small leak. The Amazon Basics has a very, very small leak, and the Kirkland is still dry. I've dried all 5 trash cans, so let's go ahead and test the next 5 brands. Just like the Kirkland brand, the Hefty bag is very well sealed. I did not notice a bag leak with the full circle until I gently laid it on the concrete. However, it definitely has a leak now. It's a very light duty bag at under 15 grams. And the Commander is holding water without any visible leaks. And the Eco is also doing a great job without any leaks. And the HDX is also very nicely sealed without any leaks. So that's 3 bags in a row. After several more minutes, the Hefty, Commander, Eco, and HDX are still without any leaks. So let's move on and test the next 5 trash bags. And the Perk trash bag is very well sealed. The Glad Force Flex is also very well sealed. Unfortunately, the steel coat has a pretty bad leak on 2 different sides of the bag. I've been told that Oxes love water, and this one is holding water without any leaks. And Hippos have an even bigger affinity for water, and the Hippo is without any water leaks. After several more minutes on the concrete, the Perk, Glad, Ox, and Hippo Sack are still doing well. Unfortunately, the Glad Max is leaking. And the Glad Max is leaking on both sides of the seam. And the Tough Bros bag also has a very small leak. And the Hold On bag is the final bag in the lineup that is well sealed. After several more minutes, there's still quite a bit of water leaking from the Glad Max. And the Tough Bros is also leaking quite a bit of water. Unfortunately, the Hold On bag appears to have a very, very small leak, and I didn't catch it earlier. And it took quite a bit of time to fill the trash bags with water, but the process for removing the water went a whole lot faster. So about half the brands are very well sealed, and most of the other bags have a very small leak. Leaks and tears oftentimes begin with a puncture. Let's go ahead and test the puncture resistance using this tester that I put together. I'll first place the tester on a weight scale, and then I'll use a drill press to measure the amount of downward force required for a 16-penny nail to puncture the trash bags. And the Rely brand really struggled at only 126 grams of force to puncture the bag. And the Neat bag weighs about twice as much as the Rely brand, and it takes over twice the force to puncture the bag at 264 grams. And the T4ing isn't quite as puncture resistant as a Neat bag at 162 grams. And the Amazon Basics performed almost as well as a Neat trash bag at 246 grams. Let's test the top of the bag first, which is a lot thicker than the bottom area of the bag. And the top area of the Kirkland is by far the most puncture resistant yet at 734 grams. Very impressive. And the main area of the bag is also the most puncture resistant bag yet at 468 grams. That's going to be very challenging to beat. And the Hefty bag performed very well at 366 grams to move into second place behind the Kirkland brand. That's about 22% less puncture resistance than the Kirkland. And the Full Circle bags are almost as puncture resistant as the Hefty bag at 352 grams. And the Commander stopped commanding quite a bit sooner than the Kirkland, Hefty, and Full Circle bags at 274 grams. And the Eco bag eked out 312 grams before getting punctured by the 16-penny nail. That's a little bit better than average. Let's test the thicker area of the HDX first. And the HDX performed very well at 454 grams for the thicker area of the bag. And the main portion of the bag is also pretty durable at 402 grams. That's good enough to move into second place behind the Kirkland. And the Perk trash bag really needs to perk up if it's going to compete well in this showdown. And 118 grams is good enough to move into last place so far in this event. Don't get mad, get glad is the motto for the Glad brand. And the Glad moves into second place behind the Kirkland at 420 grams. With a name like Steel coat, expectations are very high, and the name seems to fit on this test at 430 grams to move into second place behind the Kirkland. So the question is it ox stronger than a steel coat? Not this time, and it took 312 grams to puncture the ox. And the Hippo sack is about the same price as the ox. It also has about the same puncture resistance at 310 grams. And the Glad Force Flex Max is supposed to be stronger than the regular Glad Force Flex. And the Glad Force Flex moves into the lead over the Kirkland at 504 grams. Very impressive. With a name like Tough Bros, street cred is on the line. And it turns out that Tough Bros isn't so tough after all at only 108 grams. You'll probably want to hold off on placing a sharp object inside of the hold-on bag. And it's 120 grams or about 80% less puncture resistance than the Glad Force Flex Max. So the Glad Force Flex came out on top at 504 grams. Kirkland finished in second at 468 grams and Steel Coat 430. A high-quality trash bag will grip the top of the trash can so the bag doesn't fall down into the can when it's in use. To test this, I'll place a knot in the middle of the trash bag. I'll wrap a towel around the head of the sledgehammer to use as a ram. And the Rely trash bag did a great job of gripping the top of the trash can. And the top of the bag outlasted the bottom of the bag at 44 pounds. And the Neat bag didn't grip the top of the trash can quite as good as the Rely brand. And the bag fell into the can at 33 pounds. Without having a drawstring, the T4ing really struggled in this test. And the bag fell into the can without the scale taking notice. And the Amazon Basics bag did a great job of gripping the top of the trash can. And the top of the trash bag never did let go, but the bag finally stretched to the bottom of the can at 74 pounds. And the Kirkland bag lost grip on the trash can at 40 pounds or 34 pounds less than the Amazon Basics. And the Hefty Ultra Strong gave up sooner than the Kirkland and the Amazon Basics at 35 pounds. And the Full Circle really struggled to gain a grip on the top of the trash can at only 4 pounds. And the Commander relinquished command at only 5 pounds or 1 pound more than the Full Circle. And the Eco Trash Bag is not very stretchy and it offers a very loose fit on the top of the can. And it's over for the Eco at 2 pounds. And the HTX performed about the same as the Kirkland at 39 pounds. And the Perk gave up quite a bit sooner than average at only 19 pounds. And the Glad did a great job of holding on to the can and the bag stretched to the bottom of the can at 54 pounds. And the Steel Coat lost grip on the top of the trash can at 34 pounds. And the Ox trash bag is a beast, but the bag isn't designed to grip on the top of the trash can. Just like the Ox, the Hippo sack is not designed to grip the top of the trash can. And the Hippo sack gave up early at only 5 pounds. And it sure seems like the Glad Force Flex Max should outperform the less expensive Glad Force Flex. Unfortunately, it gave up early at only 25 pounds. I tested a different bag and had the same result once again at 25 pounds. And the Tough Bros really struggled on this test, losing grip at only 3 pounds. And the hold-on bag definitely does not offer the best top-of-can hold-on strength at only 27 pounds. So the Amazon Basics, Glad Force Flex, and Rely are the only 3 bags that maintain a grip on the top of the trash can and outlasted the bag. Kirkland and HTX also performed well at 39 and 40 pounds respectively. Let's go ahead and compare the performance of the trash bags for holding up to rips and tears. I'll first cut out an area of the trash bag. I'll then make a cut down the middle, leaving a 2-inch section that's uncut. I'll only test a single layer of each bag. And the Rely bag gave up very early at only 92 grams, so not much tear resistance. And the Neat brand offers about 8 times as much tear resistance as the Rely brand at 804 grams. If the T4ing bag ever experienced a gash, the bag will likely spill everything onto the ground. However, 34 grams is not too surprising for a very light-duty bag. And the Amazon Basics trash bag weighs almost as much as a Neat trash bag. And the Amazon Basics moves into the lead at 822 grams. And the Kirkland performed well at 546 grams, but that's a couple hundred grams short of the Amazon brand. And the Hefty performed almost the same as the Kirkland at 554 grams. And the Full Circle gave up at 442 grams to move into 5th place behind the Kirkland. And the Commander performed 30 grams better than the Full Circle at 472 grams. And the Eco Trash Bag held up well in this test, finally ending up in 2 pieces at 720 grams. And the HTX performed about the same as the Full Circle and the Commander at 464 grams. And the Perk performed about the same as the HTX at 484 grams. And the Glad Force Flex performed better than average at 642 grams. And the Steel Coat performed well in this test at 502 grams. And the Ox is a beast and it held up really well in this test, finally ending in 2 pieces at 1,586 grams. And the Hippo sack gave up a little bit sooner than most of the other bags at 330 grams. And the Glad Force Flex performed very well in this test at 876 grams to move into 2nd place. And the Tough Bros is not so tough on this test at only 24 grams. And the Hold On Trash Bag performed a little below average on this test at 346 grams. So the Ox Trash Bag dominated the competition at 1,586 grams. However, the Glad Max, Amazon Basics, and Neat also performed very well at over 800 grams. Most trash bags have 2 seams, and oftentimes, those 2 seams are the point of failure. So I'll go ahead and wrap this piece of railroad in a towel, and we'll see if any of the bags have enough strength to lift the railroad steel, which weighs around 70 pounds. And the HOLLiiWOOD brand made it to 42 pounds when both sides of the bag failed at the seam. Definitely a weak point for this bag. And the peak let go at 53 pounds, or 11 pounds better than the HOLLiiWOOD trash bag. And the T4ing trash bag continues to struggle in this showdown, experiencing failure at 37 pounds. And the Amazon Basics performed by far the best yet, finally letting go at 70 pounds. And the bag tore at the seam. And the Kirkland trash bag lifted the railroad at 74 pounds, and is the first trash bag to survive the test. And the Hefty isn't nearly as hefty as the other brands, with the seam ripping at only 36 pounds. That's about half the strength as a Kirkland. And the Full Circle is very light duty, and it gave up at only 19 pounds. And the Commander trash bag tore along the seam on both sides of the bag at 34 pounds. And the Eco also tore along the seam, but just on one side of the bag at 50 pounds. And the HDX barely edged out the Amazon Basics at 71 pounds. The bag tore along the seam, and the seam on one side of the Perk trash bag tore at 41 pounds. And the Glad trash bag tore along one of the seams at 66 pounds and tossed a railroad iron to the side. And both seams on the steel coat tore at 35 pounds, or about half the strength of the top three brands. Without the benefit of having a drawstring around the top, the Ox tore at 70 pounds. And the Hippo Sack also performed better than average at 56 pounds without the benefit of having a drawstring for added strength. And the Glad Max has a weak drawstring, but the bag itself performed very well in this test at 74 pounds. And the Tough Bros let go a little bit sooner than most of the competition at 32 pounds. And the Hold On held on long enough to outperform most of the competition at 64 pounds. So the Kirkland, Glad Max, HDX, Amazon Basics, and Ox Plastics all did well at 70 pounds or more. So which trash bag is the best? The bags are organized from least expensive to most expensive. I converted the performance metrics into an A through F rating in order to make sense of capabilities by category. And the best all-around trash bag in the showdown is the Glad Force Flex. It earned an A in every category except for trash bag failure with nuts and bolts. However, it still performed well in that category with the B+. The Kirkland and HDX bags also performed very well. I would definitely be willing to buy either of those bags. If it's all about rugged durability, I would definitely choose the Ox. While it doesn't have a drawstring, it more than makes up for it by rugged durability. I've definitely been buying the wrong trash bags, but fortunately, I now know better. All the videos in this channel, including this one, are viewer suggested. So if you have a video idea, I hope you'll take time to leave a comment. Thanks so much for watching. Please take care and look forward to next time.
The concept of trackless trains dates back to the early days of steam travel. Known as trams in North America and land or road trains in Europe and Australia, these vehicles were initially designed to serve various transportation needs and are now primarily employed in the tourist industry. Typically, these articulated vehicles operate on roads with a powered tractor unit pulling multiple unpowered cars to transport goods or people. These versatile vehicles have been used for publicity stunts such as the MGM trackless train that toured New South Wales in 1928. This gasoline-powered steam engine replica, complete with a modified Pullman car, traveled on rubber tires, enabling it to navigate both urban roads and mild off-road terrain. Many electric trams are in use today, including a Chinese tram that runs on digital tracks. However, most trams are not well suited for carrying more than a busload or two of people and lack the capability to function as all-terrain vehicles. Well, enter into the picture Robert Gilmore Letourneau, widely known as the Dean of Earth-moving for his contributions to the field of earth-moving machines. Letourneau's journey began in 1902 when he left school at the age of 14 and eventually moved from Vermont to Minnesota and then to Oregon. He took whatever jobs he could find along the way, most in skilled trades or general labor. His diverse experiences in trades such as ironmongery, welding, carpentry, farming, and mining shaped his inventive spirit. And in 1929, he purchased a used tractor and opened a company maintaining dirt and gravel roads. In 1921, he established a machine shop and engineering workshop to manufacture earth-moving equipment, and over the next 8 years, he expanded the company, simultaneously working on major projects like the Boulder Highway to the Hoover Dam and the Newell Cutoff in California. During and after the Second World War, R.G. Letourneau Inc. made a name for itself, providing the Allies with sturdy construction equipment and creating innovative designs still used today, such as the first jack-up drilling rig and straddle carrier. It's said Letourneau supplied up to 70% of the construction equipment purchased by the military during those years. The company expanded, moving its main fabrication centers to Texas. After retiring from this company, Letourneau focused on enhancing the equipment produced by his manufacturing company and embarked on a groundbreaking personal project. Just before we continue, a word from our fantastic sponsor, Squarespace. Have you ever felt the struggle of standing out online? Well, fear not. That's what Squarespace allows you to do. You can build a stunning online presence as easy as A, B, C. Squarespace has an amazing feature called Flexible Website Template. It's like having a closet full of stylish outfits for your website. You start with a template, you tweak it to match your vibe, and voila, beautiful website done. Fluid Engine is also an amazing way to do this. It's a way to drag and drop your website to make it exactly how you want it. Squarespace also just launched their newest feature, Courses. Create and sell online courses seamlessly with professional layouts and the powerful Fluid Engine editor. Turning your knowledge into income is as easy as hitting play. Head to squarespace.com for a free trial, and when you're ready to launch, visit squarespace.com/megaprojects to save 10% on your first purchase of a website or a domain using the code MEGAPROJECTS. So, why settle for the ordinary when your online presence can be extraordinary? Check out Squarespace today. And now back to today's episode. In the early 1950s, Letourneau was sponsored by the military to create a multi-purpose aircraft tow tractor, which was dubbed the Tornado. This design utilized a gas generator to provide energy to electric driving motors connected to each wheel. After the success of his electric wheel design in this setting, Letourneau took the idea further and conceptualized a fully articulated train of electric vehicles powered by a large diesel-electric generator. Just like the Tornado, each wheel would have large rubber tires and an individual motor, providing exceptional traction in any situation. Letourneau's vision bore a resemblance to modern diesel-electric trains, but with a key distinction. His overland train wouldn't rely on any fixed infrastructure. While traditional freight trains can move under their own power off tracks, their inability to turn without rails or a turntable makes operating them off track impractical. Exceptions, like the case of the Canadian National 3502 in 1998, demonstrate that emergency situations may call for impractical measures. CN 3502 was lifted from the rails and rolled down the road under its own power, where the train's engines provided emergency power for a town cut off from the power grid due to severe snowstorms. The December 1953 edition of the University News Journal, Letourneau Now, delves extensively into the topic of land trains. The cover features a striking image of a man standing beside one of the colossal tires that would be used by these trains. The image effectively conveys the immense scale of the mammoth machines in development. In the newspaper's first article, Letourneau himself emphasizes the strengths of these machines, highlighting their wide stance, low center of gravity, high tractive effort, and the capability to easily navigate terrain where tracked vehicles like tanks or bulldozers would struggle. He clarifies that he doesn't believe their diesel-electric, rubber-tired trackless train will replace traditional railroads, instead saying these vehicles offer unique logistical options that conventional trains cannot provide. Letourneau, a trailblazer in the use of large rubber tires on heavy construction equipment, had previously constructed oversized bulldozers and front loaders for military and civilian use, resembling those commonly seen on construction sites today. He would utilize his experience designing and fabricating earth movers to make the world's largest ATVs. The prototype, simply called the Torner Train, was assembled in Longview, Texas, using parts from graders and scrapers already in production. This impressive ATV hauler was quickly repurposed for nearby logging operations as a show of its versatility, and this piqued the interest of the logging company's owner. The breakthrough for Letourneau's land trains occurred in 1953 with the creation of the VC-12, a 500 horsepower tractor paired with 3 powered cargo trailers. This configuration technically classifies the VC-12 as a 16-wheel drive vehicle, proving highly effective in transporting lumber across diverse terrains, and it was much more nimble than onlookers could imagine. It managed to maintain speeds of around 20 miles per hour on rough logging roads, and even made a trip through town to show off its mobility by taking tight turns along Longview streets. The second generation of VC-12 incorporated 3 additional cargo trailers and a secondary control cab at the rear, enabling operation from either end, akin to a traditional train with engines at both ends. The military quickly took notice of the success of this massive all-terrain vehicle. The United States Army Transportation Research and Development Command, or TRADCOM, reached out for more information. Their interest stemmed from the need to address the challenges of constructing and supplying air bases in the untamed, sodden, and frozen regions of northern Canada. Specifically, the military focused on the Distant Early Warning Line, or DEW Line, an extensive radar system planned in conjunction with the Canadian government. It would span several hundred miles north of the Arctic Circle, from Alaska to Baffin Island in eastern Canada. This radar station network aimed to detect Soviet bomber or missile activity within the Arctic Circle, providing America's Strategic Air Commands with crucial response time. Existing radar defense lines were obsolete and faced seasonal disruptions from Canada's migratory geese. The modified VC-12 presented a promising solution for building new outposts in the far north, far away from industry and infrastructure. A private demonstration at the Letourneau Proving Grounds confirmed its utility. In April of 1954, TRADCOM granted Letourneau funding to build a prototype, the TC-264 snow buggy. Design and construction began almost immediately. The snow buggy rolls on 8 3-meter-tall tires, 1 electric motor driving 2 wheels each. The motors were powered by a single Allison V1710, an aircraft engine developed to power the P-38 Lightning during World War II, which was modified to run on butane. The 1,500 horsepower engine could generate over 1,100 kilowatts, more than enough to power the experimental Arcto vehicle. The buggy was first unveiled in June 1954, before being shipped to Greenland for testing. The Army was interested in evaluating the idea for moving petroleum and other oil-based necessities over ice. The TC-264's huge tires gave it incredible maneuverability on marshy tundra and snow, and provided a smooth ride on any surface. While not a proper overland train, the snow buggy was an excellent proof of concept for key design features of future overland trains, outperforming the military's expectations before being shipped back to the United States. So, with the success of the snow buggy, the VC-22 Snow Freighter was born, a larger, longer, and specially equipped vehicle tailored to overcome the challenges of the icy north. Alaska Freight Lines, a Seattle-based company contracted for logistics work in the construction of the DEW Line, hired Letourneau to construct this one-of-a-kind vehicle for them. The boxy Snow Freighter could transport 150 short tons, that's 140,000 kilograms of cargo in Arctic conditions well below zero in both Fahrenheit and centigrade. It would also ford moving rivers and snowdrifts up to 4 feet deep without difficulty. The VC-22 was constructed from parts cannibalized from previous prototypes and mass-produced 6x6 earth-moving vehicles, allowing the Letourneau to deliver the specialized ATV in a very short amount of time. Its 24 electric motors, 1 for each wheel, were powered by 2 400-horsepower Cummins NHV-12 BI-V12 diesel engines. Pulling a total of 5 40-feet-long motorized cars, the 24-wheel Snow Freighter measured in an impressive 274 feet. The VC-22's first journey began in fall of 1954, ferrying supplies for building roads, airstrips, and radar stations from Fairbanks, Alaska, to the Arctic Circle in northern Canada, a trip of over 400 miles. They weren't alone. Accompanied by over 32 conventional trucks and many bulldozers used to construct the rough road through the Alaskan wilderness that the convoy would use. In the book 18 Wheels, North to Alaska, author Cliff Bishop describes the conditions that this first convoy faced. To quote, "They had to keep the engines running 24 hours a day to keep from freezing up, and they hit heavy snowdrifts. At times, it took several cats working together to clear these snowdrifts, and it took several hours at a time to do this. The bulldozers worked full-time to keep the road going ahead of this convoy, and it was very rough going. Often, they made only 2 or 3 miles a day, and the best they could probably ever get was a little more than 20 miles in a single day." The quote ends. After making the return trip in spring of 1955, another expedition was planned for the coming fall. This convoy expected an easier trip as they no longer relied on bushwhacking bulldozers for clearance, but they'd be wrong. A number of mishaps, including trucks being abandoned due to broken axles, a deadly plane crash, and the snow freighter suffering a jackknife by a tributary to the Yukon River near Eagle, Alaska. That day, an inexperienced driver was at the helm, and during the accident, fuel lines were pinched and ruptured, starting a massive fire. The ATV's engines burned up. Now, fortunately, no one was injured during this crash or the ensuing fire. This did force Alaska Freight Lines to offload the snow freighter's trailers into semi-trucks and Cat trains bulldozers equipped with cargo sleds. The VC-22 was left behind, and it still sits abandoned near the Steese Highway outside of Fox, Alaska to this day. A land train cousin was completed in October 1955, the side dump train. This innovative vehicle would see no orders, however, and the prototype never left Letourneau's facility in Longview. This design differed substantially compared to the other land trains, resembling a cross between a grader and a dump truck. The cab and generator sat at the front, connected to a rear side dumping bucket. Each car had 6 wheels, individually driven by electric motors, making the STD an 18x18 drive ATV. The Army ordered the production of an Arctic overland train in 1954 after the snow buggy's successful testing in Greenland, but Letourneau's LCC-1 snow train wouldn't finish production until 1956 after the VC-22's demise. The snow train was a 16x16 drive vehicle with 1 tractor and 3 cars. The LCC-1 utilized the specialized snow wheels of the TC-264 with the power systems of the original Torner trains. It also included accommodations for the crew of 3 during operations and improvements on previous designs. The control cab included a powerful crane for loading and unloading cargo or removing and installing the vehicle's 3-meter-tall, 2.5-ton wheels in the field. In this and other aspects, the LCC-1's control cab resembled America's ill-fated Antarctic snow cruiser of the late 1930s, but it performed far better. When attached to its 3 cars, the snow train measured in at just over 590 feet. Unlike previous models, the LCC-1 used only one 600-horsepower diesel engine. This was more than enough for this application, making the snow train less heavy than its predecessors. The actuated control cab also improved clearance and steering on rough terrain. Despite having started production before Alaska Freight Line's VC-22, the snow train would not be completed until January of 1956. A number of features needed fine-tuning before the final product could be presented to Tradcom. The final design was somewhat lackluster, a relatively featureless train-shaped cab with gigantic tires. The massive ATV was capable of hauling up to 45 tons in total. The Army used the Tradcom Proving Grounds located in Horton, Michigan for the LCC-1's initial testing before disassembling it for shipment to Greenland for high-stress testing. During its lifespan, the snow train received many modifications, including the addition of radar equipment and an acrylic dome on its top similar to the one seen on Russia's Kharkov-Chanka Arctic cruiser. This allowed the crew 360 degrees of sight without leaving the warmth of the cab. The LCC-1 snow train made a number of voyages for Tradcom across Canada and Alaska until its final cargo run in 1962. It eventually ended up in a scrap heap in Fairbanks, Alaska, and sat there until the scrapyard's owner died in 2009. That same year, the LCC-1 was put up for auction. Mark Moore discusses the sale in his book R.G. Letourneau's Overland Trains: A Complete History. The scrapyard owner's son listed the unique machine for sale on eBay, of all places, simply titling the auction Land Train 1962. There were only 3 bids, resulting in a sale to a man in Whitehorse, Yukon Territory for $15,000. After expensive disassembly and being trucked into Canada on flatbeds, the LCC-1 was donated to the Yukon Transportation Museum located in Whitehorse. It has since been restored and is prominently displayed there today. LCC-1 was such a success both in testing and in the field that the Army signed another contract with Letourneau to fabricate an even larger land train in 1958. It would take 3 years to design, fabricate, and assemble what would become the longest off-road vehicle ever built, the TC-497 Overland Train Mark II. Like the last several overland trains, the Mark II rolled out of the workshop for preliminary testing at Letourneau's proving grounds near Longview during the last months of 1961 before being disassembled and packaged for shipping to the Army's Yuma Proving Ground in Arizona. The Mark II arrived in Yuma in February 1962 and was reassembled for testing under Project Otter for overland train terrain evaluation research. TC-497 performed very well, crisscrossing with ease over the desert hills and creek beds with 10 cargo cars and 2 power cars trailing behind it. While the concept of the Mark II was similar to all of Letourneau's overland trains, its actual design varied greatly. The large 6-wheeled cab was over 20 feet tall with its attached radar dish and was 46 feet long. The main structures of the cab and cars used welded aluminium to save on weight wherever possible. The massive electric wheels of the Mark II had the capability to turn independently, eliminating the necessity for the control cab to be actuated for steering at departure from the LCC-1. This robust ATV accommodated a crew of 6 and featured bunks, a dining room with a kitchenette, and a bathroom equipped with a unique incinerating toilet. Additionally, the Mark II was air-conditioned, making it suitable for diverse environments. Impressively, it exceeded expectations in the deserts of Arizona and could be readily adopted for cold weather conditions. Similar to the snow buggy, the Mark II did not incorporate a diesel generator, opting instead to use a Saturn X MC turbine engine from Solar Turbines Inc. While smaller than a Cummins diesel, the specialized turbine could produce 1,170 horsepower to the cab and its trailing cars. The Mark II could reach a maximum off-road speed of 20 miles per hour while towing up to 150 tons of cargo. 3 other turbine engines were located on the power cars, interspersed throughout the train, totaling at 4. They had 680 horsepower and theoretically allowed for the assembly of trains of any length. This theory, however, was never tested, as more cars were never ordered. Its maximum operational length was 570 feet. When off-road, each turbine would guzzle between 30 and 60 gallons of fuel per minute. An impressive feature of the Mark II was its regenerative braking. This allowed the engines to attach to each wheel to act as generators during braking, converting kinetic energy into electricity. However, this wasn't enough to reduce fuel consumption. Because of the massive quantities of specialized fuel needed for off-road operations, the Army began making plans to construct a portable nuclear reactor to power the electric driving engines. Various practical reasons made sure that this never became a reality. Engineers swiftly recognized the potential hazards and additional weight involved in making a mobile reactor, akin to the challenges faced in the Soviet Union's pursuit of a nuclear train concept. A unique change in design was a groundbreaking solution to the problem of such a long vehicle taking sharp corners. Precision was key in allowing the 54x54 off-roader to make multiple tight turns in succession as the train passed obstacles. To allow for precise maneuvering, the complex array of power and control wires were connected to the Mark II's cab, and they resembled more the steel cables used on large suspension bridges than power and control lines. This allowed the Mark II to utilize an innovative computer system that made each car's individual wheels turn at the same location that the control cab began turning, eliminating the need for driver judgment during maneuvers and reducing cut-in substantially. Viewers in Australia might be aware of the wide turns multi-trailer road trains make to avoid getting hung up on their own trailers while avoiding obstacles. The Mark II had a turning radius much closer to that of a single-trailer tractor-trailer, and the computer allowed the driver to worry about what was ahead rather than keeping an eye on the 12 attached cars behind him. With a full load range of 350 to 400 miles, low speeds, and an abysmal fuel consumption rate, another innovation caught the military's eye: Sikorsky aircraft sky cranes. While the helicopters only had operational ranges of around 230 miles, they could cover that distance at 120 to 150 miles per hour compared to the Mark II's rarely reached off-road maximum speed of 20 miles per hour. The rise of the helicopter during the Vietnam War spelled the end of the overland train. The military no longer had Cold War funding for experimental projects. There was a hot war on now, and it was costing more than expected. The Mark II was one of the projects cut during the early 1960s. After testing funds dried up, Project Otter was disbanded. The Mark II sat at the Yuma Proving Ground before it was listed for sale in 1969. An Arizona-based scrap dealer bought the power and cargo cars for $1.4 million. The cab of the TC-497 was driven to the front of the Yuma Proving Ground Heritage Center, where it rests today as a monument to the Army's research efforts. While no further overland trains were produced, their legacy lived on in an unusual place: monster truck racing. The owner and driver of Bigfoot, Bob Chandler, outfitted the fourth version of his famous truck with 10-foot-tall tires that may look a bit familiar. This was a stunt to beat out the competition, who claimed their trucks were the largest in the world. Chandler claims that he purchased these gigantic wheels from a Seattle scrap dealer for $1,000. Some sources say the wheels were previously used on the LCC-1 snow train, while others speculate that they came from the VC-22 or the Mark II. Regardless of their provenance, these pieces of little nose overland trains helped Bigfoot take its place in the Guinness Book of World Records as both the largest and widest monster truck. Letourneau devoted his entire life to hard work. At the age of 77, he relinquished the presidency of Letourneau Technologies, passing the reins to his eldest son. Despite stepping down, he continued working in a modest office at the company, designing bigger and better earth movers like he always had. He could almost always be found there until the spring of 1969. It was in March that he was hospitalized after a severe stroke. Letourneau would never recover, passing away on June the 1st. He was survived by his wife, daughter, and 4 sons.
What does Boeing's latest crisis tell us about their market position compared to Airbus, and how far behind are they? Will it even be possible to recover this lost ground for them?
For a company that was once considered the gold standard of commercial aviation, Boeing's reputation has clearly been compromised. Its share price fell by 20% in a month.
Well, things aren't looking that good right now, that's for sure, but there may be a thin ray of hope for Boeing after all. Stay tuned. I've already made several videos on the blowout of the MAX 9 mid-cabin door plug, which happened on the 5th of January 2024, and I will probably have to make more as the official report starts getting released. But today, I want to talk to you about what this story means for Boeing's business as a whole, and what it might mean for their future. I'm sure most of you know that there is a long list of problems that Boeing has been dealing with over the past few years, and it's fair to say that the 737 MAX 1 and the 1.5-year grounding back in 2019 definitely got the most attention. But in case you missed it, Boeing actually also stopped delivering 787s for a period even longer than that, starting from around September in 2020. That stop was caused by various quality and supplier problems which hit the 787 production, causing a stop in deliveries for nearly 2 years. What this means is that Boeing now has a 787 backlog where the involved aircraft are in need of various checks and rework before they can be delivered to their customers. As for their flagship, the huge Boeing 777X, this aircraft should have taken 7 years to develop and certify, but now instead looks certain to take at least 12 years, and that's without even being an all-new design. If we go beyond their airliners, Boeing also has a number of military and space programs which frankly aren't looking much better. These include things like the KC-46 tanker, the Starliner space vehicle, and the next Air Force One. All of these projects are currently recording losses, mostly because of agreed fixed-price contracts where Boeing themselves have to cover any unforeseen costs. But the thing is, before the MAX 9 blowout in January, it seemed like Boeing were finally beginning to put their ducks back in a row, even if they still had a lot of work to do. For example, they seem to be getting really close to certifying the 737 MAX-7, the smallest member of the MAX family, whose main operator will eventually be Southwest Airlines. On top of that, it also looked like Boeing was about to start delivering new 737 MAXes to airlines in China for the first time since early 2019. And they actually also made that happen a few weeks later in January of 2024. Now that was a big deal for Boeing because, you see, airlines and aircraft lessors only pay a very little bit of money in advance when they buy their new jets, meaning that manufacturers get almost all of their money upon delivery. And Boeing had a backlog of around 85 737 MAXes that were supposed to be delivered to Chinese carriers, meaning that they had a lot of money tied up there. Boeing's total 737 MAX inventory is today close to 200 jets, so should all get delivered within 2024, well, except for 35 of them, who are 737 MAX 7s and MAX 10s, and I'll get back to those very soon. The final good news were that the FAA certification flights for the 777X also got underway last year, which meant that Boeing restarted their production in late 2023. At a slow rate, of course, since final certification and deliveries likely won't come until 2025. So, with all of that said and done, how did Boeing actually do in 2023? Well, they definitely did better than they did in 2022, but when you compare them with Airbus, it still doesn't paint a very rosy picture. During the year before, in 2022, Boeing delivered a total of 480 aircraft, and in 2023 that number went up to 528. And by the way, 396 of those jets were 737s, including military P-8 Poseidons. That's, by the way, why we say that single-aisle aircraft are the bread and butter product of both Airbus and Boeing, since that's really where most of their profits are made. As for Airbus, in 2022 they delivered 661 jets, which rose to 735 in 2023, according to Dominic Gates in Seattle Times. This means that Airbus delivered nearly 40% more aircraft than Boeing did last year. And to make matters even worse, remember that Boeing had a lot of 737s and 787s in delivery backlog from the previous groundings? Well, it turns out that some of Boeing's 2023 deliveries actually involved quite a few jets from this backlog, so not planes coming directly from their assembly lines. Anyway, that was deliveries. So what about new orders then? Well, 2023 was actually a pretty great year for both Boeing and Airbus, thanks to really big orders from a few airlines in India.
An aviation deal for the record books in history.
Boeing got net orders for 1,314 aircraft in total, up from 774 in the year before. And Airbus broke the all-time record for new aircraft orders as they scored 2,094 net orders. That's orders minus any cancellations and conversions. That's an astounding number, but if we focus only on orders for the 737 MAX and the A320neo family, well then Airbus got nearly twice as many orders as Boeing did. Both manufacturers obviously got more orders than deliveries, which means that their order backlogs continued to grow. So Boeing now has total orders of 5,626 aircraft, while Airbus has again much more than that, sitting at 8,598. What this all means is that Airbus has beaten Boeing for the 5th year in a row now, and very little seems to be changing in that trend. But if we just ignore Airbus for a second, well, then we can see that Boeing's numbers are at least heading in the right direction. And this fact has led to a lot of analysts to suggest that, at least in the short term, Boeing should just continue doing what they're doing right now. They basically just need to keep their head down, deliver aircraft, continue work to certify new ones and look after their supply chain. And also make sure that things just continue to run as smoothly as humanly possible. Or as Dan Catchpole in Leeham News put it in an article that was published on the 4th of January, one day before the MAX 9 blowout, Boeing just needs a boring year in 2024. So, what will the MAX 9 door plug blowout do to all of these numbers and the plans that Boeing has, and what other factors are still out there potentially affecting their future? Well, I'll tell you all about that after this. Now, before we continue, let me share something with you that I find really disturbing. Did you know that there is an entire legal industry out there with companies known as data brokers who collect information about you and your family and then sells it off to the highest bidder? I actually find that offensive, and not only that, the people that they sell it to can often be spam centers or even online criminals. Luckily, today's sponsor, Incogni, reached out to me a few months back and asked if we could work together, and with their help I have managed to be removed from 55 different data brokers already, with some more still to come. You see, you can actually ask to be removed from these companies, but you have to do so manually and to each one of them separately. Now, Incogni has devised a way to do this for you, and also to continuously monitor and enforce the removal request as long as you stay with them. In my case, it has already reduced a lot of my email spam. If you want to start removing your personal data from these people as well, then click on the link here below, which is incogni.com/mentornow. If you do so, the link will provide you with an exclusive 60% discount on Incogni's annual plan. Thank you, Incogni. Now let's continue. As I said earlier, one milestone that Boeing really wanted to reach early in 2024 was the certification of the Boeing 737 MAX-7. And while this looked like a really real possibility before the MAX 9 blowout, it now instead seems to be very far away. So why is that then? Well, this has to do with a potential issue concerning the anti-ice system inside the engine nacelles on all Boeing 737 MAXes, which Boeing discovered last year. It turns out that theoretically, under certain conditions when the aircraft is flying in dry air and at higher outside temperatures, actually where anti-ice definitely shouldn't be needed anyway, leaving the engine anti-ice system switched on by mistake could cause some serious issues connected with the use of composite materials in certain parts of the engine nacelles. Specifically, running the engine anti-ice at higher than normal temperatures causes a risk of overheating, which could potentially cause damage or even the failure of the engine inlet's inner barrel. Now, I want to be really clear here. As far as we know, there have been no reports of any 737 MAX actually having any in-flight problems involving this issue. And on top of that, no airline has found any issues with the nacelles of their 737 MAX fleet in post-flight inspections or other maintenance processes. But still, this is a potential problem that has to be addressed. So, for existing, already certified 737 MAX aircraft, we pilots have been given procedures that limit the use of engine anti-ice during these type of conditions, and we also have checklists to ensure that we remember those. But this is, of course, a temporary fix. Boeing and the FAA have agreed that Boeing will introduce a redesign and updated engine nacelle design latest by May of 2026. Once that is available, then airlines with the 737 MAXes will be able to retrofit their aircraft with these updated nacelles, removing the issue completely. Again, all of this applies to existing 737 MAX aircraft like the MAX-8, the MAX-9 and the 8200. But since the smallest version, the MAX-7, haven't been certified yet, Boeing asked the FAA to grant a safety exemption, which would allow it to enter service with the same engine nacelles that are already flying with all the other MAXes. And of course, with the use of the same procedures for the pilots to mitigate that issue. Now, since that design is currently in use, Boeing thought that the odds of actually getting this exemption was pretty high. But even before the MAX 9 blowout, there was actually some skepticisms about allowing Boeing to go ahead with this new certification before the problem had been given a permanent fix. And of course, after the blowout, that skepticism just grew exponentially, even though that blowout had nothing to do with this particular issue. But it likely left a very poor taste in the mouth of the people in charge to allow a safety exception of any sort after this kind of quality problem. And a number of American lawmakers have now called on Boeing to withdraw its request for the exemption completely. And finally, Boeing did just that on the 29th of January this year. So potentially, this means that Boeing can't certify the 737 MAX-7 and the MAX-10 until this fix is completed, which could mean a delay into sometime in 2026, which would be a complete disaster. When Boeing first launched the MAX-10, the largest MAX variant, it was supposed to enter service in 2020, with the MAX-7 even earlier than that, already in 2019. So you can see why airline customers could be a bit pissed here. But there is a little bit of a bright possibility here. Like I mentioned before, the development of the 777X has also faced similar long delays. But during the development, the 777X is receiving a new composite wing. And this means that Boeing has got a lot of new competence around building composite aircraft parts. This means that hopefully they will be able to speed up the development of this new MAX engine nacelle, which is largely made from these exact composites. Because of that, Boeing CEO Dave Calhoun has recently been saying that the company can develop these new engine inlets in less than a year. If that is accurate, well then the certification and entry into service of the 737 MAX-7 will probably only be delayed by that much time, about a year, and the certification of the MAX-10 shouldn't be impacted at all since it was slated to be done around that time anyway. Of course, this is all assuming that Boeing's design and certification timeline for these updated nacelles is actually realistic. I would love to hear what you think about that in the comments below, and while you're down there, hit the like and subscribe button as well. But anyway, no matter how we turn around, we are now likely looking at more than a year more of delays, and the airline that is going to be likely most hit by this is Southwest Airlines. And of course, since they are an only 737 operator, it's very unlikely that they will be able to defect over to Airbus at this point anyway. Instead, Southwest have already switched MAX-7 delivery slots over to the -8s instead several times in the past few years, and they're now saying that they will continue doing this until the -7 is finally available, because they really still want that smaller plane. And while we're speaking of exemptions, Boeing might well need another one of those very soon. At the moment, they're still making the 767 as a freighter, but because of new emissions regulations, they won't be able to make any more of those after 2027, unless they secure an exemption for it, while they try to develop the 787 into a freighter to replace it. The problem now is that with everything that has happened, Boeing might find that it's going to be harder and harder to secure any exemptions like this in the future. In this case, they could try to re-engine the 767, which is a really interesting prospect that Björn Färm is exploring in a series of articles over on Liham News. As I always say, you should definitely check out Liham News, they're awesome. But in the grand scheme of things, as far as Boeing's competition with Airbus is concerned, this potential one-year delay to the MAX-7 won't really make any difference. But another development that has come as a direct result of the MAX-9 blowout actually does have potential to really affect all future MAX customers. And that, as I'm sure that some of you have already guessed, is the FAA's decision to limit Boeing's production output while they investigate Boeing's quality control processes. As I've explained in previous videos, Boeing has traditionally been assembling all 737s in Renton, all the way back since the late 1960s. There are currently 3 assembly lines there, although not all of them are running at full capacity. But about a year ago, Boeing announced plans for a 4th assembly line over in Everett, where they have traditionally been making their wide-body jets up until recently. There is obviously plenty of space available there since the production of the 747 stopped, and all 787s are now made in South Carolina instead. The reason for this expansion was that Boeing planned to increase its 737 production rate to 50 aircraft per month by 2025 or 26 in order to work on that backlog and thereby increase their cash flow. In various sources, Boeing's current monthly 737 output is reported to be 38 aircraft, and that's the rate that the FAA has apparently approved. But there is something here that was missed by some reports. As Aviation Week pointed out, Boeing isn't actually making 38 737s per month right now. Instead, Boeing's average for 2023 was only 28 737s per month, which is the number of actual new rollouts, not including the sales of previously stored jets. So, why did Boeing's 737 production slow down that much? Well, one explanation are the quality control issues involving Spirit's production of 737 fuselages, which I covered in detail in a recent video. But even in the last quarter of 2023, when most of those issues were already resolved, Boeing's monthly 737 output was still only 24 per month. Still, the FAA appears to have approved a monthly output of 38 737s so far, so we'll see what happened to that. Anyway, Boeing is now telling their suppliers to produce enough parts for as many as 42 jets per month in order to build back some of their inventory. And that, by the way, is something that Boeing has historically been trying to avoid at all costs in order to keep their costs of inventory down. But the thing here is, and the point that I'm trying to make, is that even though Boeing agrees that this new FAA production limit is necessary, it is a really huge blow for the company and their customers. The reason Boeing really wanted to reach an output of 50 737s per month was to avoid falling too far behind Airbus. In 2023, Airbus averaged 48 A320neo family jets per month for the entire year. And if we add to this 6 A220s that they also produce per month, we get to a monthly output of 54 single-aisle jets. That's nearly double the actual average of 737s that Boeing was producing during that same period. I have previously said that if they're not careful, Boeing could soon face a 40 to 60% market split in favor of Airbus. But the numbers that I just gave you are actually well worse than that, nearly a 33 to 66% split. And the orders that Airbus and Boeing scored in 2023 also shows that this trend is continuing. On top of this, Airbus isn't planning to stick to only 48 A320s and 6 A220s per year for very long. Instead, by 2026, when Boeing was planning to make 50 737s, Airbus is planning an output of 75 A320neos and 12 to maybe 14 A220s. What all of this means is that Boeing now must achieve two really big targets. Firstly, they need to make sure that they really can make that improved nacelle design quickly enough so that it doesn't impact the certification of the MAX-10 and limits the MAX-7 to only 1 year of further delay. But that, of course, isn't enough. Boeing also needs to satisfy the FAA and the public that their quality control practices are fixed whilst they're doing that. Without doing this, well, if they can only barely handle the backlog of 3 737 MAX variants, then adding another 2 into the mix probably won't help them. That's why United Airlines, which is a 737 MAX-10 launch customer, is now talking to Airbus about getting more or faster deliveries of A321neos instead, and to possibly also cancel or scale back their MAX-10 order, which would obviously be hugely bad news for Boeing.
We'd already started working on an alternative plan. I think this is the straw. The MAX-9 grounding is probably the straw that broke the camel's back for us. We're going to at least build a plan that doesn't have the MAX-10 in it.
Remember, as a launch customer, United was originally expecting to start receiving their first MAX-10 already back in 2020. And since airlines plan their fleet utilization extremely carefully, not to get their aircraft when they're expecting it is a huge problem. And it's not just United which is plagued by getting too few aircraft. In total, the airline industry is short of around 3,000 aircraft globally compared to pre-pandemic expectations for 2023 and 2024. But of course, that's not just because of Boeing. Obviously, supply chain problems, the war in Ukraine, and of course the pandemic itself has had huge impact on those numbers. But Boeing's continuing problems aren't making airline bosses and lessors any happier right now. On top of all of this, Boeing also have another matter to keep in mind. In September this year, they will have to renew a 10-year agreement with the IAM 751, the Seattle Union chapter of the International Association of Machinists and Aerospace Workers. Those negotiations will start in March, and they are never easy, even at the best of time. And as Liam News points out, this time, Boeing's management have basically no negotiating power. Without any plans for a new aircraft, for example, Boeing can't threaten their unions that they will build their aircraft elsewhere in the country or even abroad. So this all sounds pretty grim, doesn't it? So what can Boeing actually do? And what about those thin rays of hope that I mentioned in the beginning of the video? Well, there are actually a couple of rays, but they are quite faint. Firstly, Boeing were actually profitable in the last quarter of 2023. That was the first profitable quarter that they have had since the MAX grounding early in 2019. Of course, the MAX-9 blowout in January killed that positive momentum quickly, but they still claim that this is some progress after all of the pandemic and so many other supply chain issues that they've faced. Secondly, in terms of Boeing's competition, there's only so much Airbus can actually do to take advantage of Boeing's vulnerable position. As I've said before, United CEO Scott Kirby flew to Toulouse after the Alaska MAX blowout to talk to Airbus about getting more A321neos. He did this because he could see how this incident could delay United's MAX 10 order even further, both for certification reasons and because Boeing would simply be unable to make jets fast enough. But if they wanted to accommodate United, Airbus would also have to find delivery slots for these new aircraft. United already has orders for 130 Airbus A321neos, plus another 50 of the long-range A321XLRs. And they started taking delivery of those first A321neos only last year. But these deliveries won't end until way into the 2030s. To accelerate them, Airbus can't simply increase the plane's production rate. They have to ask other customers if they would be okay with delaying their own orders, which would be highly unlikely since, as I said before, the whole industry is short of aircraft right now. A key point here is that Airbus has to be mindful of the fact that increasing their aircraft production rate too much could also be dangerous for them. Firstly, this would expose them and their suppliers to unforeseen global events like what happened during the pandemic of 2020. Plus, in the year of 2035, when new efficient engines like the CFM RISE are expected to become available, is just about 11 years away now, which means that designing the new aircraft that will be able to use those engines isn't that far away anymore. In other words, Airbus has to balance scaling up production of its current single-aisle designs with the knowledge that they gradually will need to start scaling them down again when time comes to set up the production line for whatever aircraft comes next. But to summarize, no matter how you see it, Airbus clearly has the upper hand right now. They could afford to just basically sit back and do nothing since they have a boatload of aircraft orders and Boeing aren't really in a position to threaten them anymore. But the question is, can Boeing afford to do the same thing? Boeing used to be the manufacturer that even if the competition designed an aircraft that hit the market first, their own designs and engineering was so good that airlines often decided to wait for them and their designs instead. But with Boeing's current state and finances and the problems that they have faced over the last few years, is this still the case? Can Boeing actually take their time and eventually bring to market something really cool and innovative that can turn the tables on Airbus? Let me know what you think. I love hearing from you. And if you like these type of deep dives into the industry and want to support what we do here on the channel, then consider leaving a super chat using the dollar button here below. Or maybe buy yourself some merch or support our sponsor. But if you really want to take part in the work that we do here, well then you need to join my quality controllers over in my Patreon crew. There should be a link to do that here on the screen or in the description below, and I would love to see you in my next Zoom Hangout. Have an absolutely fantastic day. Check out these videos next, and I'll see you next time. Bye-bye.
In the beginning,
what does Boeing's latest crisis tell us about their market position compared to Airbus, and how far behind are they? Will it even be possible to have an absolutely fantastic day? Check out these videos next, and I'll see you next time. Bye-bye.
We are measuring with a statistical significance of more than 5 sigma, so a very high statistical significance that the Higgs effectively couples to the top quark, the most massive particle in the standard model.
Depending on how those different types of quark, or the electron and the muon, depending on how they connect to that Higgs field, that Higgs boson, we believe they get different masses. The symmetry between these particles is broken.
CERN scientists finally break their silence, revealing a groundbreaking discovery within its walls that challenges our understanding of the universe. This revelation, with huge consequences, has the potential to reshape our perception of reality. What have they found, and how will it change everything? Join us as we delve into the terrifying new discovery at CERN. Beauty quarks challenge fundamental laws of particle physics. In a recent study using the Large Hadron Collider, scientists at CERN noticed something unusual about a specific type of quark. Quarks are considered the basic building blocks of matter and come in different varieties called flavors. The focus of the anomaly was the beauty quark, which is known for its extremely short average lifespan of just 1.5 trillionths of a second. What puzzled the researchers was the unexpected way in which the beauty quark decayed. Normally, based on theoretical predictions and the standard model, when a beauty quark undergoes decay, it should be influenced by the weak force and transform into lighter particles called leptons. These leptons can appear as either an electron or a muon. According to the standard model, there should be an equal chance, a 50-50 probability, for the transformation into either particle during the decay process. However, the observed decay pattern did not align with these expectations. Contrary to what was expected, the data obtained from the Large Hadron Collider uncovered fascinating results. Particularly, the beauty quarks, a type of quark, displayed a decay pattern that differed significantly from what was predicted. Instead of following the anticipated 50-50 ratio, the data indicated that these quarks decayed into muons approximately 70% more frequently than into electrons. What made this anomaly even more intriguing was the striking similarity between electrons and muons. Essentially, they are nearly identical, with the only difference being their mass. The muon is approximately 200 times heavier than the electron. Typically, such a difference in mass should not have a noticeable impact on the rate of transformations during the decay process. But here's the intrigue. The unexpected behavior of beauty quarks deviating from the predicted decay pattern has led scientists to reassess and closely examine current theories in particle physics. This discovery goes beyond mere scientific interest, potentially requiring adjustments to our basic understanding of the universe's building blocks. In the standard model, forces are expected to act equally on both electrons and muons, especially during the decay of beauty quarks, influenced by the weak force. The anticipated outcome is an equal emergence of these two particles from the transformation. However, the observed deviation from this expected balance raises a significant question: the involvement of a previously undetected particle. The most plausible explanation for this anomaly is the introduction of a new type of particle into the decay process, a particle that has not yet been observed or characterized. This unexpected element
What does Boeing's latest crisis tell us about their market position compared to Airbus, and how far behind are they? Will it even be possible to recover this?
In the beginning was the code, and the code was with the computer. But the code stayed with the computer, and if we changed the computer, like for an upgrade or something, then we had to rewrite all the code, and everyone agreed that this was wasteful. What we needed was a platform on which we could develop software, capable of handling different hardware, but also not too expensive, perhaps collectively managed and developed by a team of volunteers around the world. I wonder if such a thing is possible. The creation and emergence of the operating system Unix was one of the special moments in technology history. In this video, the rise and fragmentation of Unix. In 1965, a few scientists at Bell Labs joined with peers from MIT and General Electric on a project called Multiplexed Information and Computing Service, or Multics. The idea was to create this general-purpose utility for sharing time on a computer system. Computers were super expensive, so time-sharing operating systems were developed for multiple users to efficiently share computer resources. Over time, these time-sharing systems matured into a communications tool connecting multiple users on the timeshare, with user public profiles and everything. General Electric then had a business selling timeshares for their computer systems and offered the Multics team the use of a GE 645 mainframe computer, simulated with a 635 computer. Multics experimented with some interesting concepts, for instance, the idea of having arbitrary file names and directory structures, a virtual memory system. Virtual memory is where secondary storage, like from a hard drive, can be used like as if it were a part of the main memory, the RAM. With this, the computer can handle more data than its RAM would otherwise physically allow it to handle. It was a massive improvement over existing file systems of the day, and is still used today. The Multics team tried to bring together ideas like these, which were previously floating around but not implemented, into a single commercial product. Looking back at it, they were probably trying to boil the ocean. Progress turned into a slog, too much money spent on too few people following too vague of a plan. Frustrated with the absence of a workable product, Bell Labs formally pulled out of the Multics project in 1969. Soon thereafter, GE later decided to exit the computer industry entirely, selling the division to Honeywell. Despite this, a few scientists at the Bell Labs Computing Science Research Center, Ken Thompson, Dennis Ritchie, Red Canaday, Doug McIlroy, and J.F. Osana, continued working on the project. However, the end of Multics did mean losing the GE 635 computer that they had been working with up until then. Ken Thompson had written up this little space game for that computer called Space Travel. Space Travel was an ambitious game that simulated the movement of the planets in the solar system and Pluto. The player can guide a ship through them and try to land on the planets and Pluto. A nice and mildly addicting game, but it costs $50 to $75 to play each time, per the cost of the computer timeshare. So when Thompson found a graphics-capable PDP-7 mini-computer that another department wasn't using, he decided in 1969 to rewrite the game for it. This turned out to be an ambitious project, more so since Thompson had to re-implement from scratch things like a debugging subsystem and a floating-point arithmetic package. The work took some time and had been quite tedious, with the GE Computer OS outputting paper tapes that had to be carried to the PDP-7. But after finishing that, Thompson thought to then try implementing some ideas that he had been banding around with Dennis Ritchie and Canaday. They had been talking about a new type of file system for the GE 635 computer, sketching ideas for keeping files out of each other's hair. Now quite familiar with the PDP-7, he hacked out an implementation of this file system in a day or two. From there, Thompson and others added a series of simple utilities, copying, printing, deleting, and editing files, as well as a simple command interpreter, a shell, which was a program that ran other programs. Over time, the concept of the file coalesced. A file was an interface through which you can perform certain data operations like reading or writing, but the file system itself doesn't care what was actually in the file. In doing so, the concept abstracted away the differences between various computer hardwares. Now anyone on any device can make changes to a file, and this became one of Unix's killer apps. In the summer of 1969, Ken Thompson's wife took their newborn son to see her parents, leaving Thompson with a lot of time. By the end of that summer, the whole thing had been rewritten into something separate from the original GECOS operating system this whole journey started on. They wouldn't have called it an operating system back then. Back then, it was just seen as this convenient platform for developing software on. Sometime next year, 1970, team member Brian Kernahan suggested a new name for this system, Unix, as a treacherous pun on Multics. At some point, the spelling switched to Unix. Unix on the PDP-7 offered a decent environment on which you can do programming, but the PDP-7 was an outdated mini-computer, first introduced back in 1964. Not to mention, it wasn't even theirs. So in 1970, they asked the company for a DEC PDP-11, which had then been recently introduced. Now, Thompson, Ritchie, and the team have long been asking for money for a new computer, but those requests were always rejected. This time, however, the request was granted, in part because the PDP-11 was a cheaper computer at just $65,000, and also in part, the request now had a compelling pitch attached to it, to apply the file system for the use of creating and editing text files. Now, with an actual use case, the request was eventually approved. Unix was rewritten for the PDP-11's low-level assembly language, now with a text editor and a typesetting markup language called ROF. With this, the Unix operating system was offered to the Bell Labs patent department. The patent department chose to use Unix over the competing commercial product because Thompson and Ritchie quickly endowed ROF with the ability to do line-numbered pages. What began with just 3 typists in the patent department became a popular homegrown product across the whole Bell Labs organization with multiple versions and its own support group. Unix had only been ever intended as an internal tool for Bell Labs. However, it quickly escaped the laboratory and started spreading widely throughout the computing communities. Its unexpected popularity can be attributed to a few things. First, Unix was born on relatively humble hardware. Back then, the users of the hardware were not the same as those buying it. Programmers of the day had to make do with whatever the budget could afford. A standard Unix computer back then, usually a PDP-1140, cost about $50,000 to $150,000 in 1977 dollars, depending on the memory configuration. Considering a graduate student cost about $10,000 US back then, it was a lot, but far cheaper than mainframes, which might have cost $500,000 at the minimum. Second, the Unix source code was written in an attractive higher-level programming language called C, the first such OS like this. Dennis Ritchie had produced C from B. Ken Thompson created B when he ported the Basic Combined Programming Language, or BCPL, by Martin Richards at MIT. It was far easier to program in C than in low-level machine assembly language. Because it was written in C, Unix was easy to port to different hardware architectures outside of the PDP mini-computer family. C also made Unix easier to modify and enhance. Third, and most importantly, Unix did not cost an arm and a leg to acquire. AT&T and Bell Labs sold the Unix source code to nonprofits like universities for something like a few $100s. This was in contrast to other software companies, which zealously guarded their programs' source code. And even if users were able to see the code, they were not allowed to modify it. Not the case with Unix. This behavior wasn't exactly out of Bell Labs' and AT&T's good heart. Back in 1956, AT&T settled an antitrust lawsuit by the US government, the 1956 AT&T Consent Decree. The settlement decreed that in exchange for a legal monopoly on the US telephone system, AT&T would make available all of its inventions to the academic community at no charge, or license them for fair and reasonable terms. The consent decree also barred AT&T from entering the computer business, so a computer operating system like Unix was not commercially useful for them. Funny enough, the consent decree had already facilitated the spread of one groundbreaking electronics invention a few decades earlier, the transistor, and now it has done it for another. Whichever university asked for the Unix source code from AT&T had it, or more like had it thrown at them from out the window of a passing truck. Wary of violating the decree, AT&T managers shied away from providing support to their licensees. Again, another piece of fortune, because it encouraged university students with more cleverness and time than money to work together implementing the features they wanted. By the early 1970s, Unix had gone worldwide. University computers in Australia, the United Kingdom, Belgium, and the Netherlands were running it. In November 1973, Ken Thompson and Dennis Ritchie presented the first Unix paper at the Symposium on Operating Systems Principles at Purdue University. UC Berkeley professor Bob Fabry was at the talk and obtained a copy. Since Unix then only ran on PDP mini-computers, several departments pooled their resources to get one. A few graduates and professors started working with it, and Ken Thompson himself joined Berkeley as a visiting professor in 1975 to help. He helped the team install the latest Unix version, version 6, on a newly acquired PDP 1170 mini-computer. Two students in particular became quite familiar with this Unix, Chuck Haley and Bill Joy. They worked on finishing a Pascal implementation that Thompson started, which would allow Unix to support this higher-level language. It turned out quite well, widely admired because of its excellent error handling. The Pascal implementation Thompson had apparently did not turn out error messages that were all that easy to understand. Haley and Joy also added a few utilities, including a very capable WYSIWYG text editor called X for Extended. X later became Vim, a text editor that some people like. Word got around thanks to how well the Pascal compiler recovered from errors and how fast it compiled. People started requesting their own copies of the Berkeley variant of Unix. So early in 1977, Bill Joy put together 30 copies of what he called the Berkeley Software Distribution, or BSD, and sent them out for about $50 per tape. From there, it got quite popular, which made good money for Joy since the tape costs like $10 each. A second version, Second Berkeley Software Distribution, or 2BSD, quickly followed. Then in 1978, DEC introduced a new computer called the VAX 11780, a 32-bit computer with more memory and compute power. AT&T released a version of their own Unix 32V for it, but it did not support the VAX's virtual memory capabilities. This limited processing to the computer's physical memory, diminishing its power. In a game-changing move, Bill Joy and the Turkish grad student Ozal Babaglu added that virtual memory feature and shipped it in December 1979 as 3BSD. With this, Berkeley solidified its position as the coordinating gateway for new, leading-edge Unix releases. BSD then took another big leap thanks to DARPA. Up until then, DARPA ran on a legacy mishmash of software written in different languages for different computers. In 1979, DARPA sought to consolidate to a single, quote, universal computing environment, end quote, so they can share their software across the organization. They chose Unix to be that computing environment because of how it capably handled different hardware. In 1980, Fabry received an 18-month contract from DARPA to add some features to the 3BSD release of Unix. So he, along with Bill Joy, set up a new organization called the Computer Systems Research Group, or CSRG, for this. They had a small group of core programmers, the steering committee, coordinating a global network of volunteer contributors working on the 4BSD or BSD Unix series. This new Unix had to support several of DARPA's protocols, including those for the internet. For instance, 4.2 BSD fully supported the Internet Protocol Stack TCP/IP and played a significant role in popularizing the internet as we know it today. 4.2 was very popular. Over 1,000 licenses were issued just a month after its official release in April 1983, more than all the other previous distributions combined. Momentum was accelerating. Prior to that release, though, in the summer of 1982, Bill Joy announced that he would leave the CSRG to join Sun Microsystems as a full co-founder. His work at BSD was earning him tens of thousands of dollars, but he felt the academic university atmosphere at Berkeley constrained efforts to grow. In his own words, quote, "It needed to be a commercial activity," end quote. Sun Microsystems is famous for pioneering and popularizing the workstation computer, which included Unix OS with scientific/engineering applications, the Motorola 68000 microprocessor, and other off-the-shelf hardware. They later developed their own closed-source Unix variant for their hardware, Sun OS, branched off from the 4.2 BSD version of Unix. A single Sun workstation by itself could not match up with a mainframe or even a mini-computer, but these things were meant to be networked, and in doing so became immensely valuable. Sun in turn reaped the benefits to become one of the fastest growing companies in Silicon Valley. Sun quickly rose above, but they were far from the only company to commercialize Unix. For instance, we have the small Berkeley-based software company Mount Xenu. They sold a commercially licensed version of the BSD for the DEC VAX minicomputer. The interesting name fits well with their slogan, "We know Unix backwards and forwards." They handed out some pretty fun posters and calendars at events. Other notable Unix-based startups include Santa Cruz Operation, which sold Unix variants for x86 computers, and Onyx Systems, which marketed a variant of Unix for Zilog-based personal computers. Even Microsoft got into the fun with their Unix variant for 16-bit microcomputers called Xenix. And of course, we have Steve Jobs' workstation computer startup, Next. Founded in 1985, their operating system NextStep was derived from BSD, 4.3 BSD Tahoe, if I recall correctly. Unix pioneered these powerful concepts that helped make software the powerhouse industry it is today. Its early development and foundations came about through the efforts of people just interested in it, not really making money from it. But Bill Joy clearly said the quiet part out loud. As the community grew and its potential became more apparent, the work surrounding Unix needed to be a commercial activity. 1983 marks the end of Unix's awkward growth years. A bounty of wealth laid seemingly ahead for the Unix industry, but who will reap its gains? The stage is set for the blood and fury of the Unix wars. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel and I'll see you guys next time. A human hair is about 50,000 to 100,000 nanometers wide. A virus is about 20 to 300 nanometers wide. And a fingernail grows 1 nanometer each second. When an ASML machine positions a wafer for DUV or EUV exposure, precise machinery must hit the exact right position to within a few nanometers. These margins of error boggled my mind and inspired this video. So how does an ASML lithography machine hold and move a wafer? It's magnets. But if you want to know more, let's dive in together. Alright people, let's do this one last time. An optical lithography machine is essentially a $150 million camera that uses high energy light to transfer a very complex chip design pattern onto a wafer, which is usually made of silicon, but not always. The workflow goes like this. First, we apply the photoresist, a complicated light-sensitive polymer chemical, onto the wafer using the spin coating method. After a few other preparatory steps which are important but I won't mention, it goes into the lithography exposure tool. Inside the tool we have several subcomponents: the light source, the condenser lenses, the photomask, and the objective lenses. Together, the light source and the condenser lenses make up the illumination system or illuminator. Its job is to deliver light widely, evenly, and at adequate intensity to transfer the pattern. Illumination is very important, which is why ASML dedicates multiple mirrors in its EUV machine to illumination at the cost of significant power reduction. That illuminated light then passes through or bounces off of the photomask or reticle, which contains the chip design pattern. In the early days of the semiconductor industry, the whole mask contained the whole design, but as designs got more complicated, the industry started using reticles, which represent a portion of the whole chip design. Nowadays, since almost all masks are reticles, the terms are used interchangeably. Like the wafer, the reticle is placed on a positioning table, so they can be moved to compensate for natural errors. A robot automatically handles the work of exchanging the reticle when needed. After the reticle/mask, we have the objective lens. It collects and properly focuses the light and then shrinks down the image. The light then goes on to strike the resist-coated wafer. When done right, we now have a 3D relief of a portion of the chip design on the substrate. Later, we can make that design permanent using etch processes. The wafer and its stage are pretty heavy. Fully loaded with a 300mm wafer, the stage weighs about 15 kilograms, which for illustration is the average weight of a grizzled tree kangaroo. The platform has to be able to move these wafers and their stages extremely quickly, but it also has to be capable of abruptly stopping and holding absolutely still if needed during the exposure stage. And at the exact right place too, just nanometers of margin. Machines need to have good, quote, overlay, end quote, meaning the relative position of any pattern layer relative to the others. Calculated as a percent of the feature size, overlays can get to be just a few nanometers. Errors will damage the device's capabilities and maybe even cause short circuits. Overlay requirements get even more strict when we are executing multi-patterning. That is when we use multiple exposures, positioned just right to create lines smaller than before possible. Inside the machine, the wafer stage can accelerate to as much as 20 g-forces, 20 times the force of gravity, 3 times the maximum force on a Formula 1 car, or twice the maximum permitted force in a jet fighter. At the same time, the system has to execute these fast movements and changes in movements without causing vibrations. This is for obvious reasons. Vibrations throw off the precision targeting and cause errors. ASML evolved from Philips in the Netherlands. Philips has been building semiconductors for many years. Their machines reflect this heritage. Their products were first developed in Eindhoven at Philips's NAT lab. There, the lab produced its pioneering lithography machine, the silicon repeater. Some of Philips's first wafer steppers, like the PAS 2000, used hydraulic linear motors to move their wafer stages around. These systems use a high-pressure pump to push oil through hoses and valves to generate movement. Hydraulics worked well from a precision standpoint, but lacked the necessary reliability. With all the pumps and oil around, any leak would be utterly devastating in a clean room fab. So the Philips engineers built strong seals to prevent leakage, which bulked up the device. Semiconductor customers nevertheless refused to accept the product, in part contributing to ASML's rough early years. It is an example of over-engineering to fix a problem that shouldn't have existed in the first place. After a high-profile lab incident involving a burst hydraulic oil pump, the team decided to explore electrically driven systems. To build that system, Philips tapped their experience in producing the precursors of today's optical disc technologies like the compact disc. Earlier, Philips wanted to build a gramophone-like product but for video. But since video is so much more data-dense than audio, they replaced the gramophone stylus, which physically touched its disc, with a contactless optical laser. This approach required the creation of small, precise linear motors to control the unit, reading the information reflected back from the disc. Linear motors are motors that directly convert electricity to movement without the use of a rotor. They do so using the Lorentz law, exploiting how electric and magnetic fields interact with each other to generate motion forces. NatLab engineers realized that they can apply these same technologies to position the silicon wafer. Such systems were widely successful, and ASML machines are particularly known for their precise maneuvering. As we moved into the 2000s, the industry also moved from 200mm to 300mm wafers, while also shifting to a smaller node. The lithography machines had to be re-engineered from multiple criteria. They had to accommodate larger and heavier wafers, but at the same speeds and same demands. They also needed to process smaller features. While pondering a way to handle all of these issues, ASML created the TwinScan platform, their main brand of lithography machine. We call it the TwinScan because the machine runs on a dual stage cycle, measurement and exposure. During operation, there is a wafer on each stage, clamped and secured using electrostatic forces. The chuck has tens of thousands of burls to reduce direct contact to just 2% of the wafer surface area, cutting contamination risk. At the start, we load or unload the wafer into the machine using a robot called the wafer handler. They start off with the measurement stage. In the measurement stage, the machine runs through a series of scans. These scans help the computers prepare how to align the wafer in relation to the reticle to ensure good focus and accurate overlay. Then the machine swaps the stages, rotating the wafers. The measured wafer now goes under the lens, and the machine turns on the light source until we hit the required dose of light exposure. During the swap, the machine can use the downtime to exchange the reticle, though doing so requires a new reticle alignment step. In the TwinScan, these wafer movements are coordinated by the Control Architecture Reference Model Motion Control Platform, or CARM. These are powered by a bunch of FPGAs and process controllers in a cabinet rack outside. This whole setup seems a bit obvious, but lithography machines prior to the TwinScan ran all the measurement, alignment, and exposure steps sequentially on a single wafer. Pulling off the dual stage setup was a major engineering project. The tool's architecture had to be reworked to rebalance all the new weight and mass on the machine's frame, not to mention handling all the vibrations from two processes running at the same time. It required their lens and metrology equipment, mounted on what we called the metrology frame, to be isolated from the rest of the tool's main frame using air bearings, which use highly pressurized gas to cut friction. Key to hitting throughput benchmarks is not the exposure stage, but rather the measurement stage. A DUV machine handling 175 wafers per hour, average in the market, exposes each wafer for just 20 seconds of about 2-minute cycle. The rest of the time is spent on measurement. I'm reminded of one of my favorite documentaries, Jiro Dreams of Sushi. Sushi master Jiro says, "Customers think the staff in the kitchen have it easy, and they think the master making sushi has the hardest job. But in reality, the sushi is 95% complete before the fish is brought out to me." In the TwinScan, the exposure stage is sexy, and where all the economic value is added to the chip. But when the machine sends the wafer into exposure, the sushi needs to be pretty much complete. So for ASML, figuring out the right sequence of actions during measurement is crucial in shipping a competitive machine. Today, the TwinScan name has a number of product categories. NXE TwinScan machines do EUV lithography, NXT machines run with 193nm ARF DUV light, and XT machines use 248 nanometer kerf DUV light. The NXE EUV machine can process 125 wafers an hour, so one every 2 minutes. Sophisticated DUV machines can even do 200 to 300 wafers. The numbers in the machine's name correspond to their optic systems and lenses. The machines themselves are built in a modular fashion per the customer's requirements, kind of like how PCs are. This is because machines are expected to run in customer fabs for decades. They are set up to receive upgrades to keep up with modern requirements. For this reason, there's a vast diversity even within the same category. The typical lithography machine has two movement systems inside. Systems transporting the wafer from one workstation to the other are referred to as the coarse stage. The motors handling these are referred to as long stroke because they are designed for extended range, about 1 meter, and high speed. Then we have the fine stage because they value precision over distance. As you might guess, we use what are called short stroke actuators, often voice coil motors, to handle this. To get this wide range of movements, systems are often stacked on top of each other, so the fine stage on top of the coarse stage. This is known to have caused weight issues as more stacking and movements are needed. It is interesting to review how precision movement technologies have progressed inside the machine. Early machines like the old Philips wafer stepper moved their wafers around using mechanical systems, like the aforementioned hydraulic linear motors. Tools like Canon's FPA 2000 photolithography machine for the 500 nanometer process node, introduced in 1992, used mechanical guides, kind of like rails, stacked one on top of the other for movement. But such computer-controlled systems suffered unexpected alignment errors due to friction, forces that act on the stage prior to motion. These little errors added up to create big problems. Worse, over time, that friction wore down the mechanical bearings. Then they need to be replaced, requiring expensive downtime and human intervention. In response, sometime during the 1990s and early 2000s, the industry implemented aerostatic systems. This means that they created a thin film of extremely dry air between the wafer stage and a granite slab. It is kind of like the puck on an air hockey table. This air cushioning cuts friction and reduces vibrations from the wafer stage's movements. For these machines, ASML used interferometers to track the stage's positioning, essentially lasers, mounted on sharks of course, reflecting off a mirror mounted on the side of the stage. The precision guidelines are tight, so tight that additional calculations were needed to compensate for the refractive index of the air, which changed as the stage moved around. It threw off things by as much as 1 nanometer, which was unacceptable. Nevertheless, air-based systems did a fine job for many years, but as lithography continued to advance, cleanliness benchmarks like those for EUV would eventually require the presence of a vacuum. Air systems are not viable in a vacuum, so in preparation for this, ASML in the late 2000s began switching over to suspending their wafer stages using magnetic levitation. Magnets! How do they work? According to a 2017 presentation by a vendor, the wafer stage sits on top of a 1,400 kilogram magnet plate array with over 2,200 magnets, precision placed to within 20 micrometers. 1,457 of those magnets are arranged in a Hallbach array, which is a special arrangement that strengthens the field on one side while canceling out on the other. For metrology purposes, ASML switched from lasers bouncing off the sides of the wafer stages to lasers firing down from a grid mounted over the stages. Now for NXT immersion systems, which are not in a vacuum, the metrology lasers don't have to travel so far, 15 millimeters versus as much as 300 previously. This simplified the air refractive index calculations and improved overlay. I appreciate the design thinking. Some of the challenges of the design include having to deal with errant magnetic fields interfering with the wafer, as well as cooling, which might require the use of umbilical cords or hoses impeding movement. I have seen some interesting proposals to use a single maglev system for generating both short and long stroke movements. Such a system would get rid of the stacked fine coarse stage system, saving on space and weight. It's a compelling idea and a lot of demonstrations are floating around, but the latest documentation that I have seen still shows the presence of separate electromagnetic motors for these different movements. An ASML machine has to position a 15 kilogram wafer stage with below nanometer accuracy. I, on the other hand, wear t-shirts because I have trouble buttoning my collars. Ergo, it's a little difficult for me to comprehend the insane precision necessary for this work. Something that I did not appreciate as much going into this project was just how big of a role software played. From 1989 to 2000, the number of CPUs and sensors in ASML's tools grew 6 and 8 times, respectively. That 1989 stepper, the PAS 5000, had a total of 200 million source code lines, including comments. The 2003 TwinScan has 1.25 billion lines. I know, you can't judge complexity by lines of code, but that caught my eye. This aggressive leveraging of software, the former CEO said that the team doubled in size every 4 years, is probably a key driver behind their strong performance. Worth looking at more down the line. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, and I'll see you guys next time. Building a few houses isn't enough to make a neighborhood. You also need to build the roads and sidewalks to connect them. Same with an integrated circuit. You can stick a billion transistors on an IC, but they're useless if you cannot also connect them. That is what interconnects are for. They are wires for transmitting the electrical signals between transistors and other circuit elements. For over 30 years, we used to make these interconnects and their insulating layers from aluminum and silicon dioxide respectively. But by the late 1990s, it became technically necessary to use new materials. Big technology transitions are opportunities for certain companies to pull ahead of the rest. In this case, that certain company was TSMC. In this video, we're going to look at another one of the semiconductor industry's major transitions, the transition to copper/low-K interconnects. But first, let me talk about the Asianometry Patreon. Early access members get to see new videos and selected references for those videos first. Usually videos do whatever they do, but I'm a little worried about this one since it's so niche. So early access helps a lot. Thanks, and on with the show. Since these interconnects are made from metals, the industry calls the process of laying these down metallization. As a back end of the line process, we do this metallization after we make the transistors on the wafer. The step where we produce those silicon transistors is called, what else? The front end of the line. So, at the start of metallization, we have the wafer with its transistor circuitry etched into the silicon. To get our interconnects, we then put on layers of fine metal wiring called metal layers on top of the transistors. The metal layers are separated by layers of an insulating dielectric material. The technical term for these is intermetal dielectric layers, which is as literal a name as you can possibly hope for. We will also need to cut holes into the intermetal dielectric layers to connect together multiple metal layers. We call these vias. So initially you might think of an integrated circuit as this flat, idyllic landscape of silicon circuitry. Wrong, my dudes. Today's advanced ICs are more like Hong Kong's old Kowloon walled city, layers and layers jumbled on top of one another, intricately interconnected. So we just want our interconnects to work. Is that too much to ask? Apparently not, because reality sucks. We need to talk about something known as RC delay. The RC in RC delay stands for resistance capacitance. All wires have resistance in them. Resistance impedes the flow of electrons through the metal, degrading the signal and losing energy. A wire's resistance is dependent on its material and proportional